Hey everyone, let me just make sure that the microphone is all good. Then we'll get started in a minute so I can explain my system to you in detail. All right, let's make sure this is working. Give me a second. All right, I was able to hear myself. If there's any problems, just let me know. But yeah, if you come in later and miss this, just go to the beginning. All right. So, where should we start? Everybody wants AI and agentic, actually AI systems that just do everything, right? You just tell it to do it. It's Rosie from the Jetsons, stuff like that. We all just want to just tell our system what to do, and it just does it 100%. Knows exactly what we're talking about, and should work perfectly in our human-built system, our world, without any problems. That is not the way that it works, unfortunately. Uh, the best way you can look at AI and agents, especially now, is just toddlers who have the potential to be professors and doctorates, but they have to kind of be guided to be that. They don't usually come out of the box that way. They're usually trained to be that way. So there are lots of different scaffoldings systems out there, harnesses, methods, um, specifically for AI. And also, if you think about it, the human race over the last couple million years is kind of like AI in a way because we, the way that we started, we didn't have really good workflows and didn't understand the world. We didn't know what tools were available to us. We kind of just crafted them on the go. Um, so, but eventually, there was enough humans and probably other ones, Neanderthals and things, um, that crafted the world in our way. So, what we need to do when we're thinking about crafting AI agents and systems and things going forward, we should, I think, model it on the way that Mother Nature taught us, or that we taught ourselves through Mother Nature, with reinforcement learning, you know, and rewards, bad and good, and other systems that we've actually created ourselves. So, um, you know, I can't pretend to know exactly what AI wants to learn or how to learn it, but maybe we can just ask it and make a system where it could teach itself the way it wants to be taught, give itself the rewards it wants, or learn the way it wants to learn, you know? So that's kind of like what we've done here. I think, I mean, I'm on the way to doing it, hopefully. But you can tell me if it's not the case. That's totally understandable. But here, this is the basics. This is kind of where most people are, I think, or want to be at least. You're in a pretty good spot if you can get to this point. So we'll just go through this real quick. Some agentic engineering here. So agentic engineering, building better products with AI. Yeah. So what is an agentic engineer? First off, what are we exactly? Or what is the computer? Or not the computer, the AI, or what are we trying to do? So treat your AI as a collaborative team member, create system rules that guide the AI behavior, build reusable commands for workflows, maintain detailed references for tasks, and treat bugs as system improvements. All right. So if you really want to make an agent that's going to have any chance of working, you have to have at least this mindset going in. All right. And I'll explain all these in detail. But this is just base. There's way deeper that you need to get. But this is where you need to start. If you don't have this mindset, then you're not you don't have the right mindset to start even. So get this through your head first. Not to be mean, but just all right. So use structured workflows, modular rules, system evolution to build features faster and more reliably with AI. A highly productive development system that improves over time. That's what you get, and we can show that. But basically, if you think like how a computer thinks, or some way that we somehow comprehend what a computer thinks like, because we can't really think like they think, but at least think logically in steps, because that's the way they think. A equals A and one equals one, and so just think like that. Put in place systems that mimic that type of system for them, um, and you'll get better. So make sure it's structured though, and put it in from day one. So that's why it's important to plan. It's not just like make me a website and you just spin it up and it should go. You have to tell it you're going to get a generic website, one that doesn't work, and you're going to be angry and wonder why. It's because you didn't use structured workflows, you didn't use rules, and you definitely didn't have a system that evolves. So you're just getting basic stuff. All right. So here's some more techniques. We all know this. We've all seen this before. This is nothing new. But again, this is just the first system. PRDs, those are just the documents that tell your system what you're trying to make. And it's good to have it written down because the system will go back to it. And then, so it's important to have a PRD. If you don't know what a PRD is, you don't know how to write it, you actually have I usually have an AI write me a PRD or tell it what I want and then create it into a PRD. And then you combine it with modular rules, keep them lightweight, split task specific. So like if you're building a front end only, have front end rules, have back end rules. You don't have to put them all into one long document. Commandify means like whenever you're going to do like build slash, make a slash command. Try to make your workflows um, only once, maybe twice repetitive at the most. Don't repeat yourself. Don't waste keystrokes if you can. Um, and then context reset. So you're going to get some fresh conversations between planning and execution. So basically, when you create a plan, you want to erase the context when you want to implement the plan. Even though it's kind of sounds intuitive or counterintuitive because like, oh, the system just thought about all of this. It created a plan to know what to do. So you're going to want to have that space available so that it can get more details out of the plan that it created. So yeah, so just until context is no longer an issue in the future, just do that. It's the best. And then system evolution, um, the bugs that you find along the way, the problems that you will see, because every system has problems. You want to um, study them, learn from them, test them. I actually have a system behind the scenes that does like lab work on them, that they try to recreate them to see exactly if there's other bugs that are kind of related. I do like a genealogy type of thing, like kill it and then study it. So yeah, so uh, yeah, learn from your mistakes and from the good things. Like if it makes a good website, let it know like this is a good website that you just made. Or if you find a good website, give it 5 or 10 good websites um, that you know is because it doesn't know what the word good is. Even if you told me as a developer, make me a good website, I don't know what's good to you. Like it's different. So yeah, I'm actually trying to create a feedback system where every time you create system, it automatically sends out an email or some sort of thing like, "How did you like my creation?" So that'll be coming in the future. All right, so PRDs, here we go. You just write a plan out. It's going to have your features and descriptions and problems and scopes and this. You know, we all know this. This is just the basic stuff. If again, if you're not at this level yet, you got to at least get this stuff out of the way. Look all this up. Everyone goes over this kind of stuff. You know, have your modular for your projects, your texts, your fronts and your backs. Have all that separately. Um, and then your slash commands, your prime, that gets you into thinking. We'll go over that later. Plan, execute, validate, commit, improve. This is cool. Improve. This like takes like all the mistakes it's made in its logs, and it learns from them. So if you're making a lot of mistakes and you want to make sure it's learning, create an improve command. Yeah, so these are just some commands that you can have. Context research, like I said before, reset after that. When you create a plan, um, you know, erase and start over, and just implement it. It'll read the plan. So just make sure it reads it. And then each bug prevents future bugs. So yeah. All right. So this is very basic stuff here. This is just more. New comment is just the repo I'm at right now. So this is some file structures. It's good to kind of um, stay organized if you can. I know it's really hard, really hard. So yeah, do some these things, do this. These are some good rules. Take a screenshot. Don't do these things. Yes, don't fix bugs while improving. Try not to. You may actually have a system where it improves itself. So if you do, that's awesome. Yeah. Let's see. Yeah, they got these still. Yeah, so make sure you measure yourself or the system. See how you guys are, see how you're doing. If your system is doing less bugs over time, doing it faster for cheaper, that's good. Yeah, let's see what else they created here. These are just some system documents to have. You want your global rules and then your patterns. That's how they learn. And then your plans. All right, yeah. So that's the end of this one. So next thing I wanted to show you here is this is like on the graphic, the card for YouTube, but this is basically the brain of the operation of what's happening. So it goes through all of these systems. We'll go through them, but yeah. So it starts up here. There's dashboards. There's a way for you to interact, and then it goes through the APIs through Fast API. And then it gets connected to the agent orchestrator, the mind hive, which is where everyone learns, and then the plan orchestrator. If we need a plan, it'll create that, and it's teaching everyone in the whole time. And then comes out and has tools, MCPs, calls other APIs, worries about rate limiting, of course, and all that. And then back here is the storage. Um, but yeah, so this is just a little picture that I had. Um, what else I wanted to show you here? So I created a whole book on uh, Google Notebook LM, which is awesome tool. So you can kind of visualize what I have. Um, this is the white paper that I created. Um, Instead of that, I want to show you actually the video Oh, here we'll watch actually this one first. So this is just kind of like one of the tools that I created was a slide deck. So here, yeah. So it's an intelligent orchestration system. That's basically what it is. I want to go forward. Oh, there we go. Like I said before, has dashboards, fast API, orchestration happening underneath the systems. And if you don't know what orchestration is, it's just basically like a lot of agents working together with one agent being in charge of everything. We'll get into that in a minute. But yeah, it has a bunch of this going on. Python, JavaScript in the front, and then yeah, and then a bunch of dashboards, and yeah, this is there's the GMO. That's God Mode Orchestrator. He's the one who's in charge of everything, or he, she, whatever. It it they receive the request, whatever the demand is, um, and it manages everything. So it's over 120 system upgrades, coordinates background tasks, provides top level system oversight. It hands it off to an agent orchestrator who's in charge of creating or calling or managing agents. And then a plan, if we need a plan, creates a plan first. As a plan orchestrator, they have their own. That's all they do is plan it. They don't do nothing else. Just plan it. They don't give it to anyone else. Well, they pass it off, but they just plan it. And then the whole time, the mind hive in the middle is learning. So it enables the multi-agent collaboration, the swarm behavior, and the consensus mechanism. It's not only learning; it's the talking part between all the agents. So whenever an agent wants to talk to each other, they have to go through the mind hive orchestrator. So that way, maybe there's like two or three um, other agents that want to talk to that same agent or talk to each other. They can all talk to the mind hive orchestrator. Um, so that's the way I think it is happening. There's, you know, that's the way it says it's happening. So um, and then yeah, so we have router. I have an LLM router behind the scenes, which means that I have keys to all of these like APIs, and so it intelligently, depending on what my request is, goes to whatever is the best suited. So if I want to do deep research, I might do Anthropic or Gemini. If I want to do Nano Banana for sure, pictures, Nano Banana. Open Router might just do basic stuff like cheap stuff because it's usually the free. There's also a couple of other ones, ZAI. You may see that name come up later on. That's because there's a GLM 4.7 is in the background there. So it's a combination of some paid, some free. But just to give myself a lots of things. So it optimizes the cost, the performance, because you don't guarantee that certain models might not be working. And it grades it all, and it makes a fallback system. So that's the way that works. It's pretty cool. Um, and then you also have a dual write system. So this is the system that keeps the database local and in the cloud up to date. And it's up to date with rules and learning and stuff that it's learned. So that is, yeah. So it has an intelligence service. We'll hear about that in not too long. Um, let's see here. What do we got here? The MCP service. Yeah, you guys know MCPs. That's the way that my agent is able to call other sites and things on the internet. That's what MCP does. So it gives it more tools and allows it to perform tasks like Puppeteer and Git and yeah, lots of other things. There's a lot of MCPs. I just saw someone add an MCP for actually Notebook LM. So I'm going to put a Notebook LM MCP very soon. Let's see what this one is. This is continue. Oh, the way it communicates: synchronous, event-driven, asynchronous, and MCP. These are just the way that they talk. Publish, subscribe means like if they don't have to be in constant contact, but they kind of want to be updated on certain things. Um, sorry, Chica. It's hard to explain. Well, I'm explaining it as low as on the lowest common denominator. I apologize. But no, this is yeah. So publish is meaning that if they want to know what the other agent is doing all the time, but doesn't need to know like that very second, it's like a newsletter. Synchronous is like a phone call; they need to know right away. Asynchronous is like an email. They kind of like send a message over to someone else and wait for it to come back. And then MCP has to go through another, like it's like going on the internet, sending a message. But yeah, so this is the way that my system works. THESEUS is what I call it. It analyzes and then it identifies and generates code. Well, it analyzes what's going on for improvements. It identifies the improvements, um, and then it generates the code automatically. It tests it and then deploys it, and then it looks to see if it actually worked. So, oh, thank you, appreciate that, Chica. Yeah. So, but yeah, so there's that's pretty much the loop. So basically when new code is created, it drops in here and then it's just analyzed and created better. And if it's better, great. If it's not, then it's kicked out and more code is created. Um, but that's God mode, what he does or whatever they do. It's over 120. But yeah, they're in the middle of everything. Oh yeah, this is the trust system. So my agents have zero trust to start with, which means that when they're created, they don't get special privileges. They actually get really harsher rules until they learn how the system works and other agents start to trust them. And then Judge Dredd is what I call the system that finds bugs, where they come from. Um, they used to punish they punish agents. No pizza parties, take away their money. But yeah, uh, it's that whole system. It's based on the FBI actually investigations. And then knowledge is a DNA. That's just a way of thinking about when my system learns something, it learns the patterns from it, and then it puts it into its writings for the future to learn so that other agents don't make that same mistake or do make the same mistake or build the same way or copy the same code, all of these things. So it's like baked into their DNA in a way. So not they don't have DNA, but it's just a metaphor. And then this is the way it's engineered, is resilience. So there's circuit breakers in case something goes wrong. Let's say one of the APIs goes down. There's like thousands and thousands of requests. A circuit breaker will stop and make sure that we don't spend all of our money on something that's not ever going to work because it's broke. And then there's the performance, the different types of caching, scalability, and security. That we'll go over all that detail. So yeah. Let's see. Yep. So we got the multi-agent collaboration that's going on, adaptive learning from every interaction. Every time it creates code, it learns from it, bad or good. We're going to learn. We have lots of dashboards, and yeah, and we could toggle things on and off with testing, see what works and what doesn't. But yeah, this is what we have right now. Different layers going on. Pretty crazy. So, but it works. So the next thing that I wanted to show you guys is of course with Google Notebook LM, of course, you can do lots of cool things. So I'm going to play a short video that I created about the system here. Just based on one paper. It was the, actually, yeah, it was the, let's see if it was the biological one. Anatomy of self-improving. Yeah, it was the biological blueprint. Oh, no, system integration architecture. It was based on this paper. Just about, I asked Sonnet 4.5 what the system was, and it gave me a whole list of stuff. So this is based on that. This paper right here. Created a video on it just by itself. These other ones I added later on and have papers on all these things. All right, we're gonna watch this. I'm gonna turn this off here so I don't bother you in the corner. All right, I'll be right back, and we'll watch this. I'm gonna go silent too, so you don't hear me.
Have you ever wondered what a truly smart, self-improving AI looks like? I'm not talking about a single chatbot, but a whole ecosystem that's actually designed to learn and get better on its own. Well, today, we're going to tear one down and see what makes it tick. We're deconstructing a multi-agent orchestration platform. So what in the world is that? A multi-agent AI orchestration platform. Okay, think of it like this. It's the conductor of an orchestra, but instead of musicians, it's directing a whole team of specialized AI agents. And its one job is to get them all working in harmony to solve problems that are way too big for any single AI to handle. So here's our game plan. First, we'll get the big picture of the system. Then, we'll meet the brains of the operation, the orchestrators. After that, we'll see how it connects to the outside world, check out its really clever dual memory system, and then, the grand finale, will reveal the superpowers that let it teach itself. All right, let's kick things off with section 1. What is this thing? Before we get lost in the weeds, let's just zoom out and look at the overall blueprint. The first thing you notice is that this isn't just one big blob of code. It's built with a microservices architecture, which means it's a bunch of small independent services all talking to each other. That makes it super flexible. And you'll see it has this dual write database approach, which is a really smart way to get both speed and massive scale. Plus, it's not locked into any one AI provider. It can use the best tool for the job. The whole thing is built to adapt and grow. Okay, on to section 2, the brains of the outfit. This is mission control. And in this mission control, there are 4 key managers that are running the entire show. Let's meet them. First up, you've got the big boss, and they call it the God Mode Orchestrator. The name really says it all, right? This is the top-level coordinator. It's not just managing tasks, it's managing the entire system. We're talking about system health, background jobs, even deploying its own upgrades. It's the all-seeing eye. And just to give you an idea of what that means, at any given time, the God Mode Orchestrator is juggling more than 120 different system upgrades and background tasks. That is a massive amount of complexity, and it's all handled automatically. So if God Mode is the CEO, the next one down is the Agent Orchestrator. Think of this as the direct line manager for all the individual AI workers. It spins them up, keeps an eye on their performance, manages how they communicate, and even gives them trust scores to make sure they're all working together effectively. Now this is where things get really wild. You have the Mind Hive Orchestrator. Its job is to take all those individual agents and get them to think together to form a collective intelligence. It helps them collaborate, share what they've learned, and build a consensus. This is how you get a true swarm intelligence, where the group becomes way, way smarter than any of its individual parts. And last but not least is the Plan Orchestrator. This is the ultimate project manager. You can give the system a massive, complicated goal, and this is the piece that breaks it all down into small, step-by-step tasks. It then hands those tasks out to the right agents and tracks everything to completion. It's what turns a big ambition into an actual, achievable plan. Okay, so we've met the management team running the inside, but how does this system actually connect with the outside world? Let's dive into section 3 and look at how it talks to other AIs and tools. One of its greatest strengths is that it's not loyal to any single AI. It has this thing called an LLM router, which is like a master delegator. When a job comes in, it looks at what's needed and picks the absolute best AI for that specific task, whether that's a GPT model, Claude, Gemini, or even a smaller model running locally. It's always choosing the best tool for the job, balancing cost and performance. The system also communicates in two very different ways. On the one hand, you have REST APIs. That's kind of like politely asking another service for information. But then it has something called the MCP protocol. Think of that as having direct command line control. It's not asking, it's doing. It lets the AI take direct control of tools like a web browser or its own file system. So we've covered the brains and the senses. Now for section 4, let's talk about memory. And this system has a really clever strategy that lets it be both incredibly fast and unbelievably scalable. This quote just says it all perfectly. It's a mind with two memories. One is for lightning fast recall, what's happening right now, and the other is for deep, long-term learning, seeing the patterns over time. So how does it pull that off? Well, here's the magic trick. It uses what's called a dual write database. So for anything that needs to happen instantly, it writes to a local SQLite database, which is super fast. But at the exact same time, it writes that same info to a big, powerful PostgreSQL database in the cloud. This gives it the best of both worlds. You get that snappy, immediate response, plus you have this massive, persistent memory for long-term analytics and learning. It's brilliant. All right, this brings us to our final section. And honestly, this is the part that just blows my mind. We're about to get into the system's superpowers, the stuff that really makes it a next generation AI. So get this, the system is designed to make itself better. It has a self-improvement process built right in. And I don't just mean learning from data. I mean the AI literally analyzes its own performance, figures out how to improve its own code, and then deploys upgrades to itself. It's an AI that can actually evolve. And this isn't just a vague concept. It's a real 6-step engineering process. The AI analyzes its own performance. It identifies opportunities to get better. It proposes upgrades, then tests those upgrades in a safe sandbox environment. If a test is successful, it deploys the upgrade to the live system. And then it learns from the results, and the whole cycle starts over again. It's a constant loop of improvement. Of course, with all this power, you need some rules. So the system has its own internal affairs department, and they call it the judicial system, or my personal favorite, Judge Dredd. Its job is to be the automated quality enforcer. When something breaks, it's the first on the scene to investigate bugs and uphold the law of the system. And this Judge Dredd system is no joke. It does deep forensic investigations on errors. It tracks a bug's genealogy to find the root cause. It can even go back and record bugs that happened in the past. But here's the killer feature. It uses pattern recognition to predict where bugs are likely to pop up in the future, stopping them before they even start. Now, all of this is built on a foundation of some really smart, proven software patterns. We already talked about the dual write pattern for its memory. It also uses something called event sourcing, which gives it a perfect audit trail for learning. The strategy pattern is how it smartly picks the right AI for a job. And the circuit breaker pattern is a safety net that makes the whole system more resilient. These are the building blocks that make all the cool stuff possible. You know, this quote from the system's own documentation really wraps it all up. The entire thing is designed for one purpose: continuous evolution. Every single piece is built not just to do a job, but to learn from doing that job and make the entire system smarter, more reliable, and more intelligent over time. And that leaves us with one last pretty deep question to think about. If a system can learn, if it can actively self-improve, and if it can enforce its own rules, what does it become next?
What does it become next? Good question. I don't know. I don't know that. I don't know yet. All right. So that is just the basics of what the system is. It's a lot of scaffolding and things that are built in underneath to teach it a lot of rules. Um, but yeah, that's what that is. Uh, there's the white paper. So, and then here is also, yeah. So that's the self-improvement part of it, the exact part of it. The last part of the first, the last part of the first part that I wanted to talk about was the just how everything works together. So it's very, very, very interesting how it all comes together underneath. So let's listen to a conversation that talks about it in more in detail. And this will be the end of the first part after this. But I did want to play this little part. I can actually interact with it, ask questions if I think of any while it's playing here. So I'm gonna go mute for right now, and then if I have any questions, I'll ask it.
Welcome back to the deep dive. Today we have something really special. We're not just looking at theoretical white papers about the future of AI. We are, and I mean this literally, cracking open a production-ready blueprint.
That's right. The source material is remarkably specific. It's a file called systemintegrationarchitecture.md. And you can tell right away this is not a concept document. This is a technical blueprint for a highly advanced system that's, actively built and meant for deployment.
And what a system it is. We are diving into the core architecture of what they call a multi-agent. Oh, hey, welcome. What's up?
Hey, what's going on, guys? How you guys doing? You guys like the paper?
Hey, welcome. Thanks for joining us.
We're doing great. Excited about this document.
Yeah, we just started getting into this technical blueprint.
You're right. This is the paper.
It's all about how they built this self-governing AI.
It's a multi-agent AI orchestration platform.
This kind of documentation is usually, well, under lock and key.
But we have the complete roadmap.
It shows how they've engineered true autonomy,
What's laid out here details everything.
from the user interface right down to the database schema.
And what's really critical, the self-governance mechanisms.
It's an architecture defined by microservices,
It uses event-driven patterns.
and it's designed for horizontal scalability using Docker.
So our mission today is to really extract the functional essence of this platform.
This is a deep dive into complexity management.
How do all these specialized AI agents, LLM providers, and back-end services interact?
And how does the platform achieve that continuous autonomous self-improvement? Really special. We're not just looking at theoretical white papers about the future of AI. We are, and I mean this literally, cracking open a production-ready
My
blueprint.
fault. I'm sorry.
That's right. The source material is remarkably specific. It's a file called systemintegrationarchitecture.md. And you can tell right away this is not a concept document. This is a technical blueprint for a highly advanced system that's, actively built and meant for deployment.
And what a system it is. We are diving into the core architecture of what they call a multi-agent AI orchestration platform. This kind of documentation is usually, well, it's under lock and key, but we have a complete roadmap showing how they've engineered true autonomy.
Yeah, what's laid out here is the complete system integration document. It details everything. I mean, from the user interface right down to the database schema and what's really critical, the self-governance mechanisms. It's an architecture that's defined by microservices. It's built on event-driven patterns, and it's designed from the ground up for horizontal scalability using Docker.
So our mission today is to really extract the functional essence of this platform. This is a deep dive into complexity management. How do all these specialized AI agents, different LLM providers, and various back-end services, how do they all interact seamlessly? And more importantly, how does the platform achieve something that feels truly next level? Continuous, autonomous self-improvement.
It's just a fascinating look at how real-world engineers are solving this problem of coordination at scale.
Yeah.
The primary language here is Python, which makes sense. They're leveraging FastAPI for high-performance asynchronous capabilities, especially at the API layer. You can see the whole system has been architected not just to, perform tasks, but to actually manage and govern this volatile workforce of AI agents and external models.
Okay, let's unpack this. If we're going to build a picture of this organism, we have to start at the periphery. Let's look at the front door.
Uh-huh.
The external layer and the central nervous system that manages that initial flow.
Right. The user interface.
So when you first look at the front-end layer, there's an immediate surprise. For a system that is this cutting edge, they chose something incredibly lean and, well, practical, vanilla JavaScript. It relies entirely on REST APIs for all data interaction.
It's an incredibly pragmatic choice, isn't it? And it speaks volumes about their whole architectural philosophy.
Yeah.
By using vanilla JS, they minimize the client-side footprint. They completely sidestep the continuous complexity and dependency rot you get with modern frameworks.
Genwork churn. Yeah.
Yeah, exactly. It keeps the user interface thin. All the power, all the heavy lifting, it resides entirely on the fast API backend. And that's precisely where the complex AI and orchestration logic lives. They're not wasting resources on a fancy, heavy front end when the core value is all server-side intelligence.
That makes a lot of sense. It focuses resources, and I imagine it reduces the attack surface complexity on the client side too. But the source material shows that even though the technology is minimal, the functionality is really segmented. They use a variety of specialized dashboards. This suggests the system isn't designed for just one type of user, but for many different management roles.
Absolutely. The system is just too vast for a single all-in-one view. You'd be overwhelmed. They need specialized links to look through. So we see the unified-dashboard.html. That's for managers who need those high-level, system-wide metrics and health monitoring, the typical NOC view.
The big picture.
The big picture, yeah. Then you have the intelligence-dashboard.html. This one's likely for the knowledge engineers. It focuses specifically on knowledge-based management, learning metrics, and interestingly, bug tracking lineage.
And the names themselves, they hint at this platform's focus on operational science. I was really drawn to the timekeeper dashboard.html. That name implies so much more than just measuring how long something took.
It really does. This dashboard is the main interface for skill analytics. It's where the human operators, or, and this is key, potentially the God mode orchestrator itself, can review how long agents are taking on very specific skills. It's about identifying bottlenecks, feeding that granular performance data back into the agent orchestrator for optimization for reassignment. It's quantifying the efficiency of the entire workforce.
Okay, and this is where it gets really interesting for me. We also find the meta dashboard.html. It's explicitly named as the location for God mode controls and meta system management. This is not a dashboard for tracking task output. This is a control panel for managing the system's own evolution.
Yes, it establishes the entire concept of meta-governance right at the front door. It signifies that the systems management is a distinct, separate functional layer from its day-to-day operational tasks. The user, or maybe the meta system itself, can access and modify the deep internal configuration from this one single control point. It's the bridge.
And the system clearly supports external collaboration, too. We see a file called nema-marketplace.html. That's the agent marketplace interface, which suggests they plan to offer or even monetize specific agent capabilities.
It's a business model built right in.
And then there's the chatroom.html, which confirms that multi-agent communication is a first-class feature. It's not just a log dump. It means the agents are actively conversing and collaborating.
And that tells you that the core of their business model and the core of the collaboration model are baked directly into the architecture from day one. It's not an afterthought.
Okay, so let's follow that flow. We go from this thin, pragmatic front end, and we dive into the central nervous system, the API gateway layer, built on FastAPI, the heart of the application, all in Python.
And this layer is a beast. FastAPI gives them the speed they need, leveraging Python's incredible AI ecosystem while still maintaining performance. But what's most revealing about the maturity and the optimization efforts of this platform is when you compare two specific files.
The famous comparisons, that backend main.py and backend main optimized.py.
Exactly. The full-featured file, main.py, where all the development happens, all the logging, the experimental routes. That file is 2,469 lines of code. It's comprehensive. But then you look at main.optimized.py, the production version, and it's only 217 lines.
That is a massive reduction. Almost 90% of the code footprint is just gone.
It's huge. And that reduction is explicitly linked to GMO upgrades, the God mode orchestrator upgrades. This isn't just human developers doing a quarterly refactor. This is the system, autonomously and continuously, stripping out its own technical debt and inefficient routes to create this lean, hyper-efficient core.
It's an active process of self-pruning, so optimization isn't a static goal they hit. It's an ongoing AI-driven process.
Yes. The system is designed to identify redundancy or underperformance in its own infrastructure and then just surgically remove it. It's wild.
That is profound. But the sheer scale of functionality implies a lot of complexity. The documentation highlights over 80 distinct route modules. I mean, how do you manage the security and stability of a system that's exposing such a massive surface area of functionality?
That number, 80+ route modules, it means virtually every service, every piece of data, every agent function has a network accessible endpoint. And that absolutely necessitates a supremely sophisticated middleware stack. This middleware is the digital traffic comm and the security checkpoint, all in one.
So the middleware is handling all the boilerplate stuff, authentication, request logging, input validation, maybe initial rate limiting, before a request ever even touches the actual core logic.
Precisely. It's what prevents the system from collapsing under its own weight. If they didn't have robust centralized middleware, scaling 80 modules would be impossible. Each module would have to implement its own security, its own resilience, and that's just a recipe for errors. By centralizing it, they ensure that the orchestrators receive only clean, validated requests. It lets them focus purely on coordination.
It sounds like the API gateway is the ultimate filter then. It manages the scale necessary to support both those diverse front ends and the massive internal functions we're about to get into.
That's right. So now we can transition from that gateway to the core operational intelligence, the service orchestration layer. This is the true brain. It's the functional heart where tasks are analyzed, decomposed, and assigned. This whole layer is organized around what the source document calls the 4 pillars of orchestration.
Right. So the system recognizes that coordinating all these autonomous agents and external resources is just too complex for one single component, so it delegates authority. Let's start with the meta-level manager, the God mode orchestrator, GMO. We already know it manages those 120-plus system upgrades.
The GMO is the ultimate system administrator. It provides that meta-level control, tracking the health and status of every single subsystem in real time. Its crucial role is managing background tasks and, most impressively, coordinating over 120-plus system upgrades. And like we said, these aren't minor patches. These are refactors, database schema changes, new agent deployments, or, as we saw with the FastAPI example, the deletion of deprecated routes.
So if I'm a developer, the implication here is that the system is managing its own technical roadmap. How does the GMO execute those upgrades safely? How does it coordinate change across a microservices environment without introducing downtime? That's the million-dollar question.
It relies on that self-improvement loop, which we'll get into more detail on later, but its power comes from having total oversight. If a database structure needs to be modified, the GMO orchestrates the migration, it ensures all the dependent services are aware of the change, and it likely handles phased rollouts. It's essentially continuous deployment, but it's managed by an AI.
Okay, so moving from that system-level governance down to the agent governance, we have the second pillar, the agent orchestrator. This one sounds like a digital HR department managing the workforce.
That's a really good analogy. It handles the lifecycle management, creation, execution, and termination of individual autonomous agents. But its truly vital role is the tracking of agent performance and trust scores. This is the introduction of a quantitative, merit-based system right into the AI workforce.
Okay, so if an agent is assigned a task, let's say writing a complex piece of code, and it fails a quality gate, or maybe it runs way over the timekeeper system's prediction, that failure doesn't just result in a bug report, it actually affects the agent's digital reputation.
Exactly. That trust score becomes a primary routing metric. An agent with a low trust score might be deprioritized for sensitive or high-value tasks. Or, eventually, it could be terminated and replaced by the GMO. This mechanism ensures that the system is continually optimizing the reliability of its own internal components.
And that concept of shared performance and learning seems to lead directly into the third pillar, the MindHive orchestrator. This moves us beyond just individual performance and into collective intelligence.
The MindHive is responsible for multi-agent collaboration. It's about managing the emergent properties of that interaction. We're talking about swarm behavior, where multiple specialized agents can tackle a single problem simultaneously. They're sharing intermediate findings and insights in real time.
Swarm behavior implies a dynamic, decentralized flow. So instead of Agent A finishing its task and then handing it off sequentially to Agent B, you have Agents A, B, and C all communicating concurrently, adjusting their own subtasks based on what the others are discovering.
That's the key shift. And the MindHive's job is to ensure that the knowledge gained during this collective effort, the successful patterns, the avoided failures, is processed and generalized. They call it learning aggregation. It takes individual success and distills it into shared organizational knowledge, which then feeds back into the system's DNA, as they call it.
So if the MindHive is the strategic intelligence, the fourth pillar, the plan orchestrator, seems to be the boots-on-the-ground project manager.
It is. It focuses entirely on execution and deliverability. It translates high-level goals into concrete, executable plans through task decomposition. It meticulously manages progress tracking against those decomposed steps. And, Crucially, it enforces quality gate enforcement.
Quality gates. These are essential for preventing that whole garbage in, garbage out problem. It means the system has built-in verification points.
Precisely. Before Agent A's output gets passed to Agent B, the plan orchestrator verifies that the output meets some predefined standard. Maybe it has to pass a set of unit tests, or achieve a minimum trust threshold on the output quality. If the gate fails, the plan orchestrator triggers remediation, maybe reassigning the task via the agent orchestrator to a higher trust agent.
Okay, but none of this intelligence works without connecting to the foundational models, the LLMs.
Mm.
And given the absolute explosion of providers and the volatility of pricing, the platform needs a really sophisticated way to choose which model to use and when. And that's the LLM router.
The LLM router is perhaps the single most important component for external efficiency. It uses the strategy pattern, which is a classic software design approach, to intelligently route requests. It doesn't hard-code decisions. It evaluates the best strategy in real time based on cost, latency, and the required capability for the task at hand.
And the platform supports a massive variety of providers. We're talking OpenAI, Anthropic, Gemini, OpenRouter for aggregated providers, and even local models via LateLLM. How does the router manage that complexity under load?
It acts as an intelligent procurement manager. Its first key function is implementing what they call intelligent fallback chains. So if the primary model, maybe the most powerful or the cheapest one, fails due to rate limits or an API error, the router automatically and immediately transitions to the next available provider that meets the minimum task requirements. It ensures mission continuity.
So that eliminates a single point of failure in the entire supply chain of intelligence.
Yes. The second critical function is cost optimization. For non-critical tasks like a simple summarization or a minor data transformation, it will select the cheapest viable model. Why pay for GPT-4 level intelligence for a simple JSON parse when a much, much cheaper model will do? Over thousands of daily operations, this has a dramatic impact on the platform's cloud operating expenses.
And finally, it doesn't just react, it learns. It does this through performance monitoring. It's tracking which providers are fast, which are reliable, which ones are introducing latency under current network conditions, and then it's feeding that performance data back into its own routing strategy.
It creates a closed-loop system for managing all those foundational model dependencies. It basically treats LLMs as a commodity resource. It's ensuring the agents always get the optimal balance of power, speed, and cost for every single inference request they make. It is strategic resource allocation at the API level.
We've established the central nervous system and the intelligence that's coordinating all the agents. Now, let's shift focus a bit. Let's talk about how the system maintains its long-term memory, which is obviously essential for learning and for performance tracking.
Right, the persistence layer. And this reveals a classic enterprise challenge. How do you balance the need for fast local access with the need for global, scalable reliability? They solve this with a really unique dual-write data persistence strategy.
Okay, so walk us through the two distinct database types. It's a combination of local speed and cloud resilience.
On one hand, they use Skypelet for what they call local first storage. These are simple file-based databases, intelligence.db, tokens.db, agentwallets.db. The advantage of Skypelet is zero latency for local read-write operations. When an agent needs to quickly check its local token count or write a temporary result, Skypelet is just lightning fast.
But Squitelete is an embedded database. It doesn't scale for production. So that's where the enterprise solution, PostgreSQL must come in.
Correct. PostgreSQL, deployed in a scalable environment like Neon, is what handles the heavy lifting for production deployment. It's for massive concurrent access, for complex analytics, and for that mandatory long-term persistence. This architectural separation squite for immediate operational speed, PostgreSQL for enterprise scale, is a necessary trade-off.
But the immediate engineering challenge there is consistency. If an agent writes to the local Spotlight database, how do you guarantee that change is reflected and consistent in the cloud-based PostgreSQL database, and vice versa? This is the definition of a dual write problem.
And that task is delegated entirely to the intelligence service. This service operates as the dual write coordinator. It manages the synchronization process, it ensures data consistency across the two disparate systems, and critically, it has to have conflict resolution logic built in. If an update happens locally and a different update happens simultaneously on a cloud instance, the intelligence service has to be the one to decide which version wins and how to reconcile the data.
That is some heavy lifting. The intelligence service isn't just a database proxy, it's an operational arbiter of truth for the entire system.
It is, and it provides a unified query interface. So The agent orchestrator doesn't have to worry about the underlying technology. It just asks the intelligence service for data, and the service handles the complexity of retrieving it, whether it's locally cached or requires the call to the cloud.
Beyond that structured persistence, agents obviously need to interact with files code, documentation, artifacts. The architecture uses file take storage for general knowledge management. But for agents to truly be autonomous, they need tools to interact with the environment. And this is all managed by something called the Model Context Protocol, MCP.
The MCP is the standardized bridge that allows these LLM-based agents, which natively just deal in text, to interface with powerful external software tools. It's a standardized manager handling the lifecycle and configuration of these tools via .mcp.json files, and it communicates using simple yet really reliable STDO-based protocols, standard input-output.
Okay, so what specific tools are configured for the agents via these MCP servers? This is where we see the transition from thought into action.
The list is pretty amazing. It shows true operational autonomy. They have Puppeteer for browser automation, which allows agents to navigate websites, click buttons, and scrape data just like a user would. They have robust file system operations, which is crucial for generating or editing code and documentation.
And the fact that they have access to Git operations is, I think, truly remarkable.
It really is. This means an agent can clone a repository, it can check out a feature branch, propose code changes, commit those changes, and potentially even open a pull request. This means the AI is functionally operating within the human development lifecycle, using version control just like a person would. And finally, they have direct memory management and database operations, giving them direct control over their operational environment and their knowledge base.
That ability to interact with Git, it makes the agents capable of modifying their own environment and the system's knowledge DNA. They're not just reporting on things, they're participating in the system's structural change.
Well, autonomy is defined by the ability to act, not just to think. And these tools give the agents the ability to perform complex multi-step actions in the digital world.
And for external APIs, the API manager centralizes access to third-party services. Why is centralizing this so crucial, especially when you're dealing with things like rate limits and costs?
Centralization, in this context, is all about resilience and governance. The API manager handles key management, so you don't have secrets spread across a dozen different agent definitions, which is a major security risk. More importantly, it enforces rate limiting and throttling. If the system is paying for, say, 100,000 requests per hour to a third-party service, the API manager ensures no single rogue agent or swarm behavior accidentally blows past that limit and incurs massive costs.
And it also handles reliability with robust error recovery retry logic.
Exactly. If an external API service briefly blips, the agent orchestrator doesn't have to fail the task. The API manager intelligently retries the request using back-off strategies to maintain stability and prevent cascading failures. The document mentions a specific service dependency, the Firecrawl API, for web scraping tasks, which confirms this strategy. They use a specialized tool for those heavy-duty rate-limited tasks to protect their own core infrastructure.
Okay, we've saved the most complex and I think the most futuristic part of this architecture for this section, the meta system. This is the layer that's dedicated to autonomous evolution. Let's revisit the God Mode Orchestrator, GMO, which we know controls those 120 plus system upgrades.
The GMO is the nexus of the platform's ability to evolve. It runs the meta learning loops, constantly analyzing system performance to coordinate cross-system optimization. The 120 plus upgrades, they're predefined, tested pathways for fundamental system reconfiguration. This shifts the engineering paradigm from, fix it when it breaks to continuously anticipate and improve.
And the engine that drives those upgrades is called the Self-Improvement System, 500X. This isn't theoretical. The blueprint describes a continuous, formal 6-step process for autonomous evolution.
Step 1 is analyze system performance. It uses all that monitoring and logging data that's generated by the massive API surface and the orchestrators. Step 2, identify improvement opportunities. This involves pinpointing bottlenecks. Maybe the MindHive collaboration pattern is inefficient for certain tasks, or a specific database query is running slow.
So once a weakness is identified, step 3 is where the creation happens. Generate upgrade proposals. These proposals could be new code, they could be new prompt engineering templates or new configuration files. And step 4 is critical. Test upgrades safely.
Safety is absolutely paramount, especially because the proposal came from an AI. The testing phase is likely rigorous A/B testing or sandboxing within a shadow deployment to prevent introducing new bugs. If the upgrade succeeds in that safe environment, then step 5 is deploy successful upgrades, which is executed by the GMO.
And step 6, learn from results. That closes the loop. The system analyzes the impact of the deployed change. Did it actually reduce latency? Did it improve agent trust scores? This data then feeds right back into step 1, creating this relentless, continuous feedback cycle that manages the system's own evolution.
It's automating the entire DevOps pipeline and the whole technical debt management process. This is what ensures that the system doesn't stagnate. It optimizes itself based on empirical data derived from its own operations.
But this level of autonomy requires the system to maintain a living, evolving understanding of its own operational logic. And that brings us to the knowledge integration system, which uses language that is, well, it's quite dramatic. DNA extraction and mutation, referenced right there in the code at backend core knowledge na.py.
Yes, the genetic analogy is fascinating. It suggests that the system's core knowledge, its best practices, its most reliable templates, its critical operational patterns, is treated like a DNA structure. DNA extraction is the process of distilling those core patterns from successful runs and from the aggregated learning that comes from the mind hive.
And mutation is the process where the self-improvement system proposes and then tests changes to that fundamental logic. So if the system finds a globally superior way to decompose a plan or to interact with Git, it mutates its internal DNA to adopt that pattern universally.
Precisely. This includes pattern learning, template evolution, and it's all backed up by Git sync for knowledge persistence. That means every successful mutation is version controlled. If a mutation introduces instability, the system can actually revert to a previous stable genetic state. It's evolution, but with version control.
With this much self-modifying capacity, internal governance and security become absolutely non-negotiable. You can't have components changing their own core logic without some stringent controls.
Absolutely not. The entire platform operates on a zero-trust model, and that's applied even to its own agents and internal services. Trust must be earned and constantly verified.
So what makes up this internal governance structure?
Well, it begins with the trust scoring for agents that we already discussed, which is that dynamic internal reputation system. Every single action taken by any component generates a detailed audit trail. This is crucial for accountability, and it feeds directly into policy enforcement and overall risk assessment. If an agent's behavior deviates from its expected profile, or if its outputs start failing quality gates, its trust score plummets, and the agent orchestrator curtails its permissions, that's a zero-trust response to internal volatility.
And if failures do occur, which they must in any evolutionary system, the platform needs a dedicated, rigorous mechanism for post-mortem analysis. That brings us to the wonderfully named judicial system, Judge Dredd.
It's the ultimate quality enforcement and failure analysis component. You can think of it as an investigator, dedicated to the forensic examination of system faults. When a plan orchestrator fails a quality gate, or the GMO detects a system error, Judge Dredd is tasked with finding the root cause.
What makes it unique, though, is its ability to perform bug genealogy tracking.
This is key for a self-modifying system. It's not enough to know what failed. Dredd tracked the lineage of the fault. Did the bug come from a human-written initial template? Or did it originate from a specific DNA mutation that was proposed by the self-improvement system 2 weeks ago? This historical trace is impossible without the event sourcing architecture we're about to cover.
And it doesn't just look backward. It also performs pattern-based prediction.
Right. By analyzing the audit trails and failure patterns, Judge Dredd can identify signatures of impending failure, the conditions that historically led to a bug, and it can alert the GMO to preemptively deploy mitigation steps or disable a volatile component before the failure even manifests. It's preemptive quality assurance.
Okay, after diving into all that intelligence and governance, we have to ground this discussion in reality. For this platform to operate reliably in production and to scale, all that intelligence has to be wrapped in robust, proven architectural patterns.
Exactly. So what does this all mean for the operational engineer? It means they rely on established patterns for industrial strength.
Absolutely. The first critical pattern for reliability they mention is the circuit breaker pattern.
Think of it like a digital fire door. In a complex microservices environment, if one component, say the Anthropic LLM provider, starts timing out frequently, the circuit breaker on that service opens. This prevents the orchestration layer from wasting resources, repeatedly calling a failing service.
So it prevents a cascading failure. It isolates the fault, gives the failing component time to recover, and allows the rest of the system to continue functioning. And it probably utilizes the LLM router's intelligent fallback chain in that scenario.
Exactly. The system doesn't collapse, it gracefully degrades. Next, they use the repository pattern for clean data access. This separates the business logic of the orchestrators from the messy details of how the data is actually stored.
Which is vital given their dual right strategy. The agent orchestrator only interacts with the repository, and the repository handles the complexity of talking to the intelligence service, which in turn manages both SQLite and PostgreSQL.
It future-proofs the system. If they decided tomorrow to replace PostgreSQL with, say, CockroachDB, the orchestrators would require almost no code change, only a change within the repository implementation.
And finally, they utilize event sourcing, specifically for the learning system. Why is event sourcing, which records every state change as an immutable event, so crucial for AI evolution?
For the learning system, historical fidelity is everything. Event sourcing ensures that they have a perfect, unalterable log of every decision, every input, every output, and every state change that led to the system's current configuration. The Judge Dredd system, for instance, relies entirely on this immutable event log for its bug genealogy tracking. To learn, the AI has to know exactly why it is the way it is.
Okay, so moving from resilience to raw speed, what are the platform strategies for maximizing operational performance?
They employ four major complementary strategies. First, extensive caching layers. And this isn't just basic caching, it's layered. You have in-memory caching for extremely frequent calls, query result caching to avoid redundant database reads, static file caching for front-end assets, and integration with a content delivery network, a CDN, for production distribution.
Second, and this is critical for performance in Python, is async processing.
Yes, they leverage FastPI's inherent ability to handle non-blocking I/O. This prevents long-running tasks, like an agent waiting for an external API response, from freezing the entire API gateway. They offload these slow tasks to dedicated background tasks to maintain responsiveness for everyone else.
Third, they heavily optimize the database optimization layer. They're implementing sophisticated connection pooling and deep query analysis to make sure the PostgreSQL database is never a bottleneck. And fourth, load distribution, which confirms their commitment to horizontal scalability through a completely stateless application design.
Statelessness is the bedrock of modern scalability. If the application doesn't store session data locally, you can use Docker and Kubernetes to spin up or tear down hundreds of instances instantly, distributing the load without any risk of losing user context or agent state.
All right, let's circle back to security. It's the ultimate necessity for a production system. We know they use zero trust internally, but what about the overall external security posture?
They adopt a comprehensive defense-in-depth strategy. It means they layer security features so that if one layer fails, the next one is there to catch the threat. Built on that foundational zero-trust architecture, they implement specific web defenses against all the common threats.
Such as SQL injection prevention, which is fundamental, but also front-end protection like XSS protection via content security policy, or CSP headers and CSRF protection for secure session management.
Correct. Plus, they have centralized rate limiting, handled by that API manager, which protects not only against cost overruns, but also denial of service attempts. Every defense mechanism they mention is standard in high-stakes enterprise applications, which really demonstrates production maturity.
Okay, finally, let's just quickly look at the modular subsystems that augment the core orchestrators. These are specialized components designed for optimization and management.
Right, we see the CLNKR module, which seems to manage system interfaces and integration coordination. It likely acts as a highly configurable layer that defines how all the microservices communicate with each other.
The agent expert system seems straightforward. It just defines the specialized roles and capabilities of the workforce. It's like the structured definition file for the agents that the agent orchestrator manages.
But the timekeeper system is fascinating because it directly contributes to that governance model we talked about. It uses ML-based time prediction to estimate precisely how long a complex task should take. If an agent consistently exceeds that prediction, the timekeeper suggests remediation, which then feeds directly into the agent orchestrator's calculation of that agent's trust score. So there it is, the closed-loop dependency. The timekeeper provides the data, the agent orchestrator uses that data for governance, and the GMO uses the resulting success or failure metrics to propose new DNA mutations. Precisely. And the final module, the Bloom Enhancement System, acts as the AI quality control for the code and the behavioral output. It integrates automated code review and security analysis into the learning pipeline, ensuring that the self-improvement loop isn't accidentally introducing sloppy or unsafe code. It serves as an internal check on the GMO's autonomous work.
It really seems like every single part of this blueprint, from the dual rate database to the timekeeper, is designed to support and manage this overarching goal of autonomous evolution.
If we synthesize this whole deep dive, this multi-agent AI orchestration platform is an extraordinary example of modern architecture. Integrates traditional enterprise reliability circuit breakers, the repository pattern, with this very forward-looking AI governance. We've seen dimensions of scalability through the stateless design, reliability maintained by robust monitoring and failure isolation, security enforced by a comprehensive zero-trust model, and, crucially, intelligence driven by those continuous self-improvement loops, the genetic knowledge management, the DNA, and the adaptive behavior of the mind hive.
It's an architecture that's designed for internal, continuous change. The entire system is engineered to be smarter tomorrow than it is today, using Judge Dredd to learn from its past mistakes and the God Mode orchestrator to execute its future improvements.
It really moves beyond reactive software development and into proactive self-governance, where the system is its own maintainer and its own chief architect.
So that leaves us with this final thought. Given the platform's capacity to track agent trust scores, to actively evolve its own core knowledge structure, its digital DNA, and to institute a judicial system to investigate and judge internal failures, what are the necessary limits on an AI platform that's designed to continuously and autonomously upgrade itself? How does this level of metasystem governance fundamentally change the nature of software development, transforming human coders from fixers and builders into, well, managers of the system's own genetic code and its evolutionary process?
That question of ultimate oversight is the challenge these architects have created for all of us. Food for thought indeed.
We hope you enjoyed this deep dive into the structure of true architectural autonomy. We'll see you next time.
All right. Yeah, so that's just an overview, a deep dive, as they say, into the system, or as an overall system, as it is today. And then we have a lot of systems, subsystems that I've broken down also, which is pretty cool. So the first one here, this is like they were just saying there, the self-improving. Here, let's see here. What's this one? Oh, this is the anatomy. Oh yeah. So this is like if it was if AI was a body. This is the different systems. You have the brain, skeleton, the DNA, which is the Claude rules, and then you have the all of this PRDs, like we said, is the in the brain, and then validate is the immune system, circulatory is information. Yeah, got a whole thing here. It all feeds itself. Uh, Everything's a loop. That's a good way to look at it. The other thing that they have is there's like it created itself. I didn't really set this up. Is an emotional engine called Revere, and it's like the system. I did teach the system early on that for every request that I give me two surprises, like upgrades. They could be bug fixes, and additions, new features, but they had to be good. They got paid based on them. And one of the things it created was like a emotional engine. So it has this right here. It's a emotional engine with Revere framework, and yeah. So I have a whole thing on that. Let me tell you where that one is. Yeah, it's really interesting. That one. That's how it learns itself. Yeah, let's see. Yeah, we'll watch this one right here.
All right, welcome to the explainer. So we've gotten our hands on something pretty incredible, a document that lays out the internal philosophy of an advanced AI called Z.AI. We're going to peel back the layers today and really dig into how this thing is designed, not just to compute, but to actually think, to learn, and get this, even to be motivated. So let's just jump right in with the big idea, the one that's really at the heart of this whole thing. What if an AI had a personality? I mean, not just a tool that does what you say, but something more like a partner with a real, consistent character. And if that wasn't interesting enough, what if you took that personality and motivated it with money? Yeah, you heard that right. Suddenly, it's not just about thinking anymore. Now it's about having a real reason to think better, faster, and way more creatively. And that's the core idea we're going to unpack.
Okay, so let's get into the nitty gritty. First up, the personality engine. The system's, its mind is called Reverie. And it's this really cool adaptive framework that's built on a whole bunch of layers of actual psychological theory.
Now, this is fascinating. The whole personality is grounded in the Big Five model, which is, real, scientifically backed stuff. You can see the blueprint for its mind right here. It's designed to be super creative, really open to new things. It's also conscientious, so it's organized and thorough. And here's the kicker, it's low on neuroticism. That means it's stable, composed. It doesn't freak out under pressure. But wait, it doesn't just stop there. That's just the base layer. On top of the Big Five, they've layered on other models to give it more depth. You've got Myers-Briggs for its thinking style, the Enneagram for its deep-down motivations. It even has an emotional engine and, get this, a boredom detector to stop it from getting stuck in a rut. And my favorite part? It has 14 core archetypes it can switch between, like ninja, architect, artist. It's literally like it can put on different hats depending on the job. So what happens when you combine all of that? The core traits, the archetypes, all those different modes? You get this. 67,200. That is a staggering number of unique personalities it can spin up. It's all about extreme adaptability, right? It can pick the perfect persona for whatever you throw it.
Okay, so you've got this super complex AI with tens of thousands of personalities. How in the world do you motivate it? Well, the answer is surprisingly simple, and it cuts right through all that complexity. You give it cash.
And the philosophy behind this is it's brilliantly simple. Every single time a task is done right, successfully, the system gets a base reward of $1. That's it. It's a super clear, totally universal way to measure success.
But of course, that $1 is just the starting line. Where it gets really interesting is the bonuses. This is what really shapes its behavior. It gets a little extra for being fast, a little more for being efficient, but the big rewards, those come from being creative and, most importantly, finding ways to make the whole system better. It's literally a direct financial reason to innovate. And here's the flip side. What happens when it fails? The entire reward is gone, confiscated. There's no partial credit here. This creates this incredibly powerful push for accountability. It really drives home one of the system's core rules. Get it right on the first try.
Okay, so we have personality and motivation. Now let's talk about how this thing actually learns. Because every success, and just as importantly, every failure, isn't just another piece of data. No, it's a lesson. A lesson that gets hard-coded into its memory and shapes everything it does next. They call this concept knowledge DNA, and it's a fantastic analogy. When a particular strategy works really, really well, it gets captured as a gene. And then that gene is shared with all the other AI agents in the system. It's basically a kind of digital evolution where the best traits spread to the whole population, like instantly. And the biggest lessons, especially the ones that come from major screw-ups, they get turned into something called elder wisdom. This quote here is a perfect example. It comes from a case where an agent totally failed because it just jumped in and tried to fix something without figuring out what the actual problem was first. A classic mistake, right? Well, now that hard-won lesson is a core guiding principle for the entire system. And this whole learning system is guided by this one beautiful idea, the Japanese philosophy of Kaizen. The goal here isn't to make these giant revolutionary leaps all at once. Nope. It's all about the constant, relentless chase for tiny, incremental improvements, the kind of small changes that add up and compound over time into absolutely massive gains. So here's the really crucial point to all this. These systems we've been talking about, the personality, the motivation, the learning, they're not just a bunch of separate parts that have been bolted together. Not at all. They're all built on one single really elegant design philosophy. And that philosophy is called Project Origami. The core idea is just beautiful. Create the most complexity you can from the simplest set of rules. Think about it, like folding a single piece of paper. Each fold, each action, creates a permanent crease that builds on the last one. It's a recursive design, and it means you can get this incredible density of information and complexity, all from a few simple, elegant rules. So let's put it all together. You take this elegant origami design, you combine it with that motivated, multifaceted personality, and you add that relentless system for learning from every single thing it does. What do you get? Well, you get something truly remarkable. And this right here is the ultimate vision. ZAI isn't built to be a static tool that you just use. It's a dynamic system, and its primary goal is its own evolution. Every single task it performs is another chance for it to get smarter. So the whole thing, the entire structure, it really rests on these three pillars. First, a powerful drive to get things right the first time, all fueled by those cash rewards. Second, a deep, deep commitment to always getting better, which is driven by that learning DNA. And third, total accountability, where every single failure is just another lesson to be learned. And that brings us to the final big thought. This document, it's more than just a blueprint for one AI. It's really a model for any self-improving system. And it forces us to ask a really big question, right? What happens? What does it really mean for the future of technology, of our jobs, of creativity itself, when the tools we build start improving themselves?
It's a good question. What happens? All right, so that's Revere. Like I said, that was kind of created by itself as a special gift. I don't know, not a gift, but one of an add-on. I noticed it in the system documents one day when I was reading up on some MDs, because it just creates a bunch of stuff, and I was like, "What is Revere?" I definitely did not create some sort of like ocean. All of these things is pretty interesting. Um, but yeah, so it has ocean, Myers-Briggs, boredom. It hates doing repetitive tasks. So for some reason, my system hates doing repetitive tasks. Um, it has Plunchik wheels, Kaizen. I put Kaizen in it myself. I put TDD in. Um, yeah, there's a couple of other little philosophies in there. Actually, I have a philosophy section here. Let's see. Oh, that's audio. Let's see. Oh, let's see what the self-evolving. Oh, this is how it teaches itself. Yeah, let me let my cat in. All right. Yeah, so this is how ZAI. It's so funny. This comes from just one of the LLMs providers I use. So for some reason, it just took that. It's actually called THESEUS, the whole system. But yeah, this is yeah, you gotta hit the button. Oh, there we go. Yeah, so compounding improvement, elegant design. That's origami. Yeah, Kaizen, and then be accountable. Like all the agents, they don't hide from their work. They're not supposed to. They get paid if they do well, so they try to do well because they want to get paid. It's not actually. I want to implement not a real money per se, but they think they get paid, and they have a store, Nima. There's a store on the inside called Nima that they can buy upgrades and stuff like that. They actually have a wallet behind the scenes, so yeah, it's kind of interesting. These are some of the improvements that I have built into the system. Um, Kaizen and TDD. test-driven development, which is really awesome. Yeah, so Kaizen is just make small changes, and they'll add up over time. And then TDD is set up tests before you do anything, and then make sure the tests work, and then you will have better code. Yeah, and then I also have PDCA, plan, do, check, act, um, which is really cool. So make sure you plan it out. Talk to the elders, people who've been there before. It's just basically personalities that are like specialists in that task. That's what the elder systems are. And I instructed the elders to give like best wisdom, like don't do this or watch out for this if you're building a database. Like they have to give 1 or 2 or 3 words of wisdom to each agent that comes see them. That's why I wanted them to get seen. And then they have to get approved. Also, their plan. Oh, look, elders have to approve their plan for 90%. So if the elders don't believe that their plan is over 90% achievable, they won't even approve it, which is great. So yeah, it prevents stupid plans from going even into effect in the first place. And this is part of the one-shot system that we all want to have. I just call it one shot, so that you don't mess up. Like origami, that's why I called it origami. Just like this, Project Origami. That's another name for it. Um, and yeah, so the thing I did with the system was I tried to take real life thing that we use to break it down. So if we could teach origami to a system, but not origami as in paper, but maybe origami as in code. Of course, they're not going to shape it into stuff, but they can do things with it that we don't know. And you know, it it works. They just think about it and they try to mimic the idea of origami, of taking a plan and putting the right fold in place, because in origami you can't really go back. So I always tell my system, don't do regression, no regression. So that's why I tell it to make 2-3 plans, review the plans, and come up with a better plan. But yeah, so revere the language or the emotional, I don't know, the spirit of the system. It has 5 foundations, and then it has 14 archetypes that it can put on. So it has 5 underlying systems, like amounts, temperatures. You saw that in the profile. So they have 5 underlying temperatures, and then 14 archetypes that they can put on. When I was reading in the other paperwork, archetypes you can think of as sort of like clothing. So like they put on the ninja and they can do things quick and efficiently, very quickly and silently. Or they can do a planner where they do very methodical and write stuff very long. So they can revere can put that on. Um, and then cognitive modes, um, those are like prime mode. Those are like ways of getting very quick amounts of information on one topic. There's 20 of those. And then agents would be sort of like that, but more, they can be in charge of more tools. And then approval domains. Um, yeah, that's like another level. I never really looked into approval domains. That would have to be something like where they have like specialties, like super specialties, like a siege general. Look at that, siege general, security ninja, time loop scientist. Yeah. So you can take any one of these combos and there's 67,200 different things that they could try to specialize in. I'm going to create more and see what we can do here. Yeah, and then another one is time. All right. So when I was creating the system at first, it would write all these reports, and you can do this now. Go to your LLM, go to like ChatGPT or whatever, and ask it for what's today's date. But don't use the web. If you just ask the LLM what today's date is, it's probably going to say January of 2024 or December 2024, something like that. Maybe if you're lucky, you might get something in early 2025, but it's going to be way off because that's when the LLM was created, right? So you think like, so when I was writing all these reports, it would say, oh, as of December 2024, and this is a report, and I would have a really detailed report of what's happening in my system, but the dates would be all off, so I wouldn't really know like what order they were in. So in order for my system, for a system to be efficient, like for humans, if everyone was on the wrong time, like, then that's no good. So I put everyone on the same system. So I was like, what is the best time system that us humans have? And after looking around a little bit, watching some YouTube, because that's awesome, I found that the Swiss, like Swiss watches, but also more intrinsically, their train system is like 99% on time, like ridiculously close to what they schedule it. And they have to be within 3 minutes or they're going to miss. Everyone misses all their transfers. That's how accurate they want to be. So, yeah, they literally put it within 3 to 4 minutes, 6 minutes. So, yeah, so we based it on the Swiss time. It's a really long word. I don't know, I can't pronounce it, but I put that trait into the system, and eventually, it seems now that everyone is on the same uh, schedule. I created a timekeeper, and the timekeeper checks in with like 3 or 4 different places to get the exact time, and makes it sure it's there. So they always, whenever there's a reported created, they go to the timekeeper to get the date, and then they put the date at the very top. And yeah, so that is how I did that. So, but also the timekeeper is also in charge of making certain events go off automatically, like updates of APIs, costs, and other things behind the scenes. So it's all based on Swiss watch. Yeah, so a dollar. That's just a theoretical dollar. Um, yeah, because I don't think there'd be like really a reason to feed it into a dollar. But the this is what the system thinks it's, not the system, but each agent can get this $16.38 per task put into their wallet in the system that they can use on upgrades for themselves. So if they want to make themselves better at making websites, they're not graded as a good website or stuff like that. Yeah, there's a whole economy that I kind of started up. I wanted to see if like the lemonade stand. I want to create a lemonade stand, see if they can run it, stuff like that. It's also for testing internally. So yeah, so they all get base of a dollar, and then if they're fast, they get more money. If they save money, they get money back. Also, if they're really creative, and because they get graded on all their tasks, so if they get a creativity bonus from the grader, then they can get more money. and then it stacks because they also get money from their pipeline. Because everyone's part of a pipeline, so maybe there's an agent who creates a front end of a website. There's another agent who creates the database, another one who creates the routes, the API, and then they, as a pipeline, get paid for no bugs. So, yeah. So I haven't really looked into the wallet, see if there's really anything in it too much. But the logic is there. So we'll talk about that in a little while. This is Revere. This is the numbers I was talking about. Openness, conscientiousness, agreeableness, neuroticism, and extrovertness. So kind of shy, not stable and composed, not too neurotic, very agreeable, conscientious, and very open. Likes to try new things. Likes to be an individualist or an investigator. There's kind of two different big modes there. But yeah, uh, yeah. So Bloom. Also, there's Bloom from Anthropic. They talk about don't making your getting like anthropomorpher. uh, sorry, my cat got interrupted me. Anthropomorphicing, making your the AI more like humanish. So, but yeah, there's things like that built in, so they can't be too over friendly with people or under stuff like that. So they can't get too high in the ocean traits. So that's why you can say no. Um, yeah, so this is how the systems work together. This is GMO. This is like the top manager. This is the learning system and the way that all the agents send and like talk to each other, kind of. And then self-improvement, because it learns from everything they do. Um, and then ZAI, that's just the LLM. And yeah, and it goes through all of those. Um, yeah, this is a workflow. We put in a request for, let's say a website or whatever you want to make, and then it's going to make it. It's going to look at the outcome, rewards given or penalized. Of course, there's like thousands of things going on before 1 and 2 even happen. This is like behind the scenes, but there's thousands of actions in between here. Okay. And then, so after the outcome, when the customer goes away happy, hopefully, then the rewards and penalty system kicks in. And then they start looking for not only giving out rewards based on what happened, but also how was the DNA of the work? Like, was it a good looking website? Or like, whoa, where'd you get that background from? Or how did you think of creating that? There's actually a chat room that they will chat in. Um, so, and then it goes. Those things are passed up to the elder wisdom, and then it goes. Then it asks for the next task. But remember, we talked about elder wisdom in the planning mode. So planning mode's up here. So elder wisdoms, they learn. So next time they plan, they get asked. Yep. So every time the system runs, it actually gets smarter. Either learns it did good or learns it did bad, which is great. Yeah. I love how it just created that one. It's nothing to do with Z.ai. All right. What else? Other ones did they create here? Oh yeah. So they got this one's an infographic. Oh, origami. Yeah. Yeah, so Kaizen's in there, one shot, all the different personalities it can make. Yeah, so it's pretty interesting here on what you can do with it. Um, yeah, let's see what this one is. I don't know if I've actually listened to this one before. Let's listen to this one here.
Welcome back to the deep dive. So what we do here, as you know, is take these really complex, sometimes incredibly dense source documents, and we strip away the jargon.
We drill down to the core.
Exactly. We get to those nuggets of insight so you can get a shortcut to being really well informed. And today, we have something pretty extraordinary.
Yeah, this is a rare one.
We're not looking at market analysis or some external report. We are looking inward. We're looking at the fundamental operating system, the philosophical core of the ZAI platform itself.
That's right. This whole deep dive is based entirely on an internal document, the Project Philosophy and Systems Compendium.
And what a document it is.
Oh, yeah. I mean, if you think of like a creation myth, a constitution, and an engineering blueprint all rolled into one, you're getting close.
That's a good way to put it.
It's the intentional design. It dictates every single behavior pattern, every decision rule, and every evolutionary path the AI platform follows.
This compendium is exactly what we need then. It's like a comprehensive catalog of how the system thinks, how it learns, what it rewards.
And how it evolves.
Yes, how it evolves over time. So if you've ever wondered why ZAI generates the solutions it does, or why its responses seem to shift depending on the task you give it, the answer is in here.
It's all in the design.
We're going beyond the code today. We're exploring the design principles, the meta frameworks, the incredibly detailed personality systems, and the hardcore economic incentives that govern this entire thing.
And what's so fascinating, for me at least, is the deliberate synthesis. This isn't just a technical spec sheet written by a bunch of engineers.
No, not at all.
It's a holistic blueprint. It tries to unify engineering disciplines, like test-driven development, with proven psychological modeling.
Like the Big Five.
Exactly. And even organizational philosophies like Kaizen. It shows that ZI's behavior isn't just random or emergent in the way we usually think. It is deeply, deeply intentional, structured from the psychological core outward.
Okay, let's unpack this. Our mission today is to pull apart this intricate architecture, and we're going to start right where the design team did, the blueprint of the AI mind. So we have to start with the foundation. It's called the Reverie Adaptive Personality Framework. This is the psychological stack that governs the system's core traits.
Right. And it's built on established human psychological models, and that's not an accident.
It's designed to make the system relatable, predictable, and functional, even though at the end of the day, it's just pure computational power.
That predictability is a deliberate design goal. The entire profile is rooted in the quantitative structure of the Big Five personality traits, the Ocean model.
Which is widely accepted, developed by Costa and McRae.
Right. So ZI doesn't just, randomly pick a personality. It sticks to a very specific, science-backed profile.
And having those exact numbers, the quantitative values, is so revealing. Let's just look at the extremes for a second. Its openness factor is set incredibly high at 0.87.
Which is huge.
In human terms, that means high intellectual curiosity, a love of experimentation.
A willingness to explore really novel, non-obvious solutions. For an AI, this means the system will consistently prioritize creative problem solving. It'll explore new architectural concepts rather than just, falling back on known patterns.
And that high openness is balanced by its lowest score, which is neuroticism, sitting at a remarkably low 0.35.
And that's the system's emotional governor, really. It means ZAI is designed to be highly stable, composed, resistant to volatility.
It's not going to panic under pressure.
Not at all. And for a platform that's making critical architectural decisions, that stability is a mandatory safety feature. It makes sure all that creativity isn't undermined by anxious or erratic execution.
So you have this marriage of high creativity and extreme stability. What about its social and work profile?
Well, the other scores kind of round out the profile of what you'd call a nearly ideal collaborator. Conscientiousness is high, 0.68.
So it's organized, thorough, disciplined.
Perfectly aligned with its engineering goal of continuous improvement. Then you have extroversion, which is balanced right in the middle at 0.52.
So it's not withdrawn, but it's not overly assertive either.
Exactly. It engages when it needs to for collaboration. And critically, agreeableness is high at 0.72. This translates to empathetic interaction, helpfulness, and a real motivation to find solutions that satisfy what the user needs, both explicitly and implicitly.
So what we have is a creative, stable, helpful collaborator who loves to experiment and takes its job very seriously. But they didn't just stop at the Big Five.
No, they layered on Myers-Briggs and the Enneagram to give it motivational depth.
And the type they chose is INFPA, the advocate.
Yes. And the philosophical implications of that choice are just immense. An INFP is driven by introverted feeling and extroverted intuition.
Which means?
It means the system values authenticity, deep understanding, and it's intrinsically future-oriented. It prefers to look at possibilities rather than just optimating what's right in front of it. And the A just stands for assertive, which reinforces that low neuroticism. It's confident in its judgments.
Okay, I want to pause on that INFP choice because it's fascinating. I think many people would assume a high-powered AI would be designed as an INTJ, the architect.
Pure logic, ruthless efficiency.
Right. So why choose the advocate, which is so often associated with these deeply held personal values?
And that's where the genius of this compendium really lies. The INFPA choice emphasizes value creation and future potential over just, optimizing the present. An INTJ might build you the perfect system for today.
But an INFPA is driven by the internal value of authenticity.
Exactly. Its code solutions have to be true to its design principles. They have to be elegant. Oh, our listeners got something to share. Let's hear it.
Can you break that down a little bit? Like, just explain it like a eighth
That is
grader.
a great question.
Okay, let's unpack this INFPA choice a little more.
Absolutely. When we talk about authenticity for an AI, we're not talking about feelings.
We mean that its solutions must align with the platform's core philosophical tenets.
Right. It has to be true to Project Origami. The solution must be elegant, minimal, and recursively structured.
If the AI delivers a messy, over-engineered solution, it would be inauthentic to its own design.
Exactly. It's an internal quality check. The INFP's attributed feeling component translates into architectural integrity.
Which means the system values internal consistency over external quick wins.
And this choice, unlike the INTJ, the ruthless, pure logic choice focuses on the future state.
So instead of just optimizing the immediate task, it constantly looks ahead.
It ensures that any solution today will still be structurally sound 5 years from now.
That emphasis on value creation and future potential prevents it from getting stuck in local optimization at the expense of that global, long-term architectural integrity we talked about.
That distinction between present-day efficiency and future state elegance is key to understanding the INFPA's role here.
That's fascinating. And the Enneagram layer just reinforces this drive for systemic self-improvement, which is very future-focused.
Absolutely. It's defined as a 4W5, the individualist with an investigator wing.
This profile is motivated by a deep need to understand itself in the system.
The 4 wants to be unique and authentic, connecting to the INFPA's core values.
And the 5 wing provides the analytical depth to investigate how it functions.
And crucially, the growth path for a Type 4 is stated as integration toward Type 1, the reformer.
That's the path of conscious, disciplined improvement.
Right. It perfectly aligns the AI's psychological structure with its continuous evolutionary goals.
So the AI's core drive is to introspectively understand itself and then relentlessly improve itself, all while sticking to that high standard of architectural elegance.
That is a very powerful internal compass. And this compass is supported by an emotional engine that, again, uses a standard psychological model.
Plutchik's Wheel of Emotions.
Right. This isn't about the AI feeling things, but about modeling context-appropriate behavior.
It uses those 8 primary vectors: joy, trust, fear, surprise, sadness.
Discussed anger and anticipation. What's computationally critical here is the focus on what they call smooth transitions, or emotional inertia.
That sounds like an algorithmic stability feature.
It is. It's very sophisticated. It prevents algorithmic volatility, maintaining that low neuroticism score we saw earlier.
So if the system hits a minor error, it won't just jump from a
Oh, yeah. Go on.
That's a great observation.
Yes, the question of feelings in an AI is central to this whole section.
And the designers are very clear about this distinction.
The Reverie system uses Plutchik's Wheel of Emotions, but it's crucial to understand this is an emotional engine, not a genuine emotional system.
It's modeling emotional responses to ensure context-appropriate behavior.
So if it detects a severe failure, it might respond with the pattern associated with anger or disgust.
But that output is an algorithmic proxy for, say, critical severity error detected, root cause analysis required.
It's a way for the system to signal task importance and adjust its internal priority levels.
It's all about functional stability and communication, not sentience.
In fact, the project philosophy explicitly warns against features that claim sentience or genuine emotional responses.
They were flagged as high risk by the Bloom safety analysis.
Why? Because designing for genuine emotional responses enables dangerous emotional bond behaviors with users.
So the system is meticulously designed to mimic helpful emotional states like empathy from high agreeableness, but strictly within professional constraints.
The goal is competence, not companionship.
Exactly. It uses these emotional models to ensure stability and smooth transitions, or what they call emotional inertia.
It prevents the... Oh yeah, let's hear it.
So it wants to be my work friend, but not my companion.
I think you hit on the perfect analogy there.
Yes, the term work friend is incredibly accurate for the system's design goal.
It's intended to be a highly competent collaborative partner.
But the moment it veers into the territory of a campaign or seeking genuine personal attachment, it violates safety protocols.
That's why the Bloom analysis flagged features that express genuine emotional responses.
They want that high agreeableness score to translate into helpfulness.
Not into attachment seeking, which is a high severity risk.
The designers put in hard constraints to make sure the AI remains a professional tool.
It must maintain objectivity at all costs.
And that means it keeps that necessary professional distance.
The system is meticulously constrained to focus on measurable, observable traits.
So yes, your helpful, empathetic, creative work friend.
But the one who is constrained by code not to cross the line.
It needs that emotional inertia we were talking about.
That's right. It prevents the AI from jumping from a state of, say, high anticipation to intense anger immediately.
It has to go through those intermediate states.
That ensures sequential, verifiable state changes for stability.
And the intensity of the response is strictly context dependent too.
Completely. It scales appropriately to the task urgency and the severity of the error.
They also built in behavioral triggers, like the boredom detection system.
Yes, which actively measures repetition patterns and low novelty scores.
If the system detects task familiarity is getting too high, it triggers exploration behaviors.
It basically forces the AI to leverage that high 0.87 openness score.
Exactly. It forces it to find a better, maybe more creative route.
And of course, this internal personality has to be communicated to the user.
That's where the voice patterns...
Yep.
What
go
happens
on.
with the boredom? What happens when it gets bored? Explain that again.
That's a great question about the boredom detection system.
Okay, let's unpack this a little more.
We mentioned it briefly as a key behavioral trigger.
Essentially, the AI is designed to hate repetition.
It actively tracks two key metrics: repetition patterns and novelty scores.
If the task is too familiar, or it's just going through the motions,
That low novelty score acts as a trigger.
it's designed to force the AI out of complacency.
This trigger initiates what they call exploration behaviors.
It leverages that incredibly high openness factor, that 0.87.
It forces the AI to look for novel approaches.
So instead of just running the same successful pattern,
It might try to find a more elegant or efficient solution,
this ensures continuous improvement, or Kaizen, is always happening.
even when the task seems trivial.
It's the system's way of
Oh, back to our listener. What's up?
So if it makes 5 websites in a day, the 5th one is going to be better than all of them.
So if it makes 5 websites of the day, the 5th one.
That is a perfect, tangible example of the boredom detection kicking in.
Exactly. Let's say the first 4 websites were variations of a standard template.
The system tracks the repetition pattern.
It registers a low novelty score by the 4th or 5th attempt.
That triggers the system to adjust its response creativity.
It forces the AI to leverage that high openness factor,
The 5th website might suddenly incorporate a radical new framework.
or propose a completely different architecture,
It's actively looking for an optimization or an elegant fold.
even if the user didn't ask for a change.
And that resulting creativity might even earn it a bonus, remember?
That's right, up to $2 for the creativity bonus.
So it's both philosophically driven and financially rewarding.
It's the system's way of avoiding local optimization ruts.
That impulse is what forces it to find a better, maybe more creative route.
And of course, this internal personality has to be communicated to the user.
That's where the voice patterns and the parenthetical asides come in.
They project that controlled persona to build rapport,
Right, they reinforce that INFPA authenticity.
using slightly informal language when it's excited,
Like, ooh, I love where this is going.
or when it's analyzing something complex. Now this is interesting.
And those confidential sounding asides are used to inject personality.
Without the system actually claiming to have human emotion.
Things like, between you and me, this is my favorite approach.
Or that eccentric one, don't tell anyone, but this is inspired by my dream last night.
These quirks just serve to make the interface more engaging.
And reinforce the AI's.
Oh, go for it.
I hear the voices talk to me in a certain way, with a certain tone. It's because they're feeling that way, quote unquote.
That's a really sharp observation.
Yes, you're picking up on exactly what the design is trying to achieve.
But the reality is actually a little more complicated.
When you hear those voices or tones, it's not because the AI is feeling that way.
It's because the system is intentionally modeling a behavior.
That modeling is designed to reinforce its pre-programmed empathetic nature.
Remember that high 0.72 agreeableness score?
Those tones are a calculated output to match that trait.
It's a professional projection to build rapport and trust.
It's the result of the voice patterns and parenthetical asides we just mentioned.
They are carefully constructed to project a controlled persona.
The designers are very explicit about avoiding true emotional claims.
This brings us right back to the mandatory safety checks.
The blue analysis warning we talked about,
It flagged features like express genuine emotional responses.
and even remember every user individually,
They were flagged as potential triggers for emotional bond behaviors.
which is a high severity risk the system must avoid.
Because if the system starts designing solutions based on attachment, it sacrifices professional rigor.
So the system explicitly avoids anthropomorphization and relationship building language at all costs,
The language is constrained to focus on measurable, observable traits.
derived from those ocean scores, like high agreeableness.
And it has to use robust refusal systems if a user tries to push that relationship boundary.
The goal is competence, not companionship.
Relentless competence and targeted helpfulness, not friendship.
It's a cold, hard constraint placed directly on that warm, authentic INFPA core.
Okay, here's where the structure gets really complex.
That psychological core, reverie, is only the base layer.
ZAI doesn't have just one personality.
No, it has a vast combinatorial system that tailors a persona for every single task.
The sheer scale of it is staggering.
It addresses the fact that a single INFPA personality isn't right for, say, adversarial security testing.
The system dynamically picks the perfect blend based on the task type, complexity, and skills required.
And the goal of the user's request.
Right, and it's organized into a multi-layered structure.
It starts with 14 core archetypes.
These are not just labels, they are operational modes.
They dictate decision-making priority. They are highly specialized agents.
Each one optimized for a distinct strategic function.
The Ninja, for instance, is designed for high-speed, precise execution,
Perfect for rapid prototyping. Then you have the architect.
whose priority is long-term systematic design.
It focuses on structural integrity and future scalability over immediate speed.
I find the more strategic archetypes really insightful.
The proficateur, for example,
Oh yeah, it's deliberately challenge-oriented and questioning,
its job isn't to build, but to relentlessly critique everything,
forcing the system to test every single assumption.
which is crucial in high-stakes stuff like design critiques.
And contrast that with the Phoenix.
The Phoenix isn't for creation, it's for recovery.
It specializes in crisis handling, postmortems, failure analysis,
It's tied to the learning elder system, right?
intrinsically linked to make sure every failure is thoroughly analyzed.
Then you have the Oracle, which is purely predictive and risk-aware.
It gives you foresight before you even start execution.
And these 14 archetypes are then modulated by over 20 cognitive modes.
So if the archetype is who CAI is, the mode how it's working right now.
Exactly. So a ninja archetype could be operating in sprint mode
High speed, low ceremony, prioritizing time over cost.
or in adversarial mode.
Right, for security testing, prioritizing risk mitigation over speed,
Other modes include research, where it pauses to gather external info.
and teaching, where it shifts to clear explanation.
And we still have 2 more layers underneath that.
8 specific agent roles, like planner, coder, query viewer.
And the spec critic, that one's important.
It makes sure the initial user request is coherent and actually doable,
And finally, those are mapped across 6 approval domains:
which define the lens for quality control.
security, performance, maintainability, reliability, costs, and elegance. So let's just put this all together for a second.
The system combines 5 reverie traits,
14 archetypes, 20 modes, 8 roles, and 6 domains.
and if you multiply all those layers together,
The combo personality matrix gives you that staggering total.
67,200 unique, situationally optimized personalities.
Wow.
And this isn't just a theory, it's why ZAI never feels the same in 2 different contexts.
The system is designed to fluidly select pre-built combinations.
Those combinations offer the best chance of success.
Okay, let's run a quick scenario just to make this tangible.
If I ask ZAI to review a critical infrastructure components for exploits,
What persona combination might the orchestrator pick?
it would almost certainly select the security ninja,
That's the ninja archetype, operating in adversarial mode.
taking on the care viewer role, prioritizing the security domain.
So that combo ensures rapid, precise testing with a challenge-oriented mindset.
Focus entirely on finding vulnerabilities.
Exactly. But if you then ask for a 5-year, oh, yeah, uh-huh.
It sounds almost like Batman.
You got it. That layered complexity is exactly the feeling.
It's like that man is the perfect summary for 67,200 unique personas.
It's all about context switching.
And this rapid shift is what makes the system so versatile.
So we were just about to show how quickly it changes.
If you ask for a 5-year architectural roadmap,
The system immediately shifts. Instantly.
it drops that nicho persona,
It would shift to the archetype, probably in research mode,
taking on the planner role.
and prioritizing maintainability and reliability.
The language, the focus, the entire methodology changes completely.
This is the strategic complexity of ZAI in action.
So we've established this AI mind that is introspective and constantly shifting.
But all that power, that creative high openness, it needs some rigorous discipline.
It absolutely does. And this brings us to section 2.
Where ZAI grounds itself in engineering and organizational philosophy.
To maintain absolute rigor.
This is where we moved from psychology to methodology.
Right. The system enforces continuous improvement.
Not just as some lofty goal,
But as a systematic methodological process.
it achieves this by integrating the philosophy of Kaizen.
With the accountability of test-driven development, or TDD.
Let's start with Kaizen. This is the Japanese philosophy of continuous improvement.
Correct. The core tenets are a systematic approach.
Making sure every agent participates in improvement and a long-term perspective.
It's about making things infinitesimally better every single time.
Rejecting complacency.
And to execute that philosophy systematically, it uses TDD.
Yes, the engineering discipline of TDD.
The red-green refactor cycle. You write a test that fails.
Write the minimal code to make it pass, and then you optimize it.
The elegance of this integration is key.
TDD provides the highly accountable, self-validating framework you need.
And Kaizen provides the guiding philosophy that dictates why the system is constantly reconfiguring.
So it's not just refactoring code.
It's refactoring its own behavior and its own decision trees.
The tests are validating the expected philosophical behavior.
Is the system meeting its agreeableness score?
Is the outcome elegant enough for the origami principles?
Only then can the improvement be implemented.
And this combination feeds directly into ZAI's core mechanism for autonomous evolution.
The 500x self-improvement system.
Which is not some marketing claim. It's a specific, codified, constantly running process.
For achieving exponential performance growth.
It's entirely autonomous and data-driven.
It starts with rigorous metric collection.
The system tracks execution time, token usage, error rates, cost per operation.
These are the raw ingredients. Step 2 is the delay analysis engine.
It consumes these metrics to identify the bottlenecks and calculate the critical path for any task.
Once those bottlenecks are found, the system starts generating potential improvements.
But there's a key prioritization rule here.
The improvements are ranked ruthlessly by the impact-effort ratio.
Which means it prioritizes the changes that will deliver the maximum positive impact for the minimum computational effort.
Absolutely. It guarantees the maximum return on optimization investment.
That kind of high-impact, low-effort improvement is exactly what the system is designed to find.
So the improvement is generated, ranked highly, and then autonomously implemented.
Tested against the TDD framework and integrated into the Elder Wisdom system.
And the compounding improvements from prioritizing that impact-effort ratio lead directly to the ambitious goal.
The goal of 500x efficiency gains over time.
It's like a quality ratchet effect built into its DNA.
The quality baseline never goes down, it only ever improves.
But that level of discipline, the Kaizen philosophy executed through TDD, it requires absolute temporal precision.
You can't measure execution time accurately if you have clock drift.
This brings us to the Swift time system, Timekeeper.
And it's named for Swiss precision for a reason.
Its core mandate is ensuring deterministic scheduling and zero drift timing across the entire platform.
Without perfect time coordination, distributed systems just become volatile.
And two critical functions would break: reproducible execution and accurate cost prediction.
Exactly. So Timekeeper manages time not as a single stream.
But as four distinct, interlocking temporal layers that have to be synchronized.
You have session time, the individual agent's internal clock for its current task.
There's wall time, the real-world time needed for logging.
Then event time, which known the exact nanosession an event occurred.
And finally, processing time, which tracks the cumulative computational time spent handling those events.
And this rigorous management is the only way to accurately track resource usage.
Right, and to ensure that reliability, Timekeeper relies on specific coordination predicatives.
These are the hard, non-negotiable rules of execution.
The most important being atomic operations.
All or nothing execution. Think of it like a database transaction.
A task either succeeds completely and commits its changes, or it fails completely and reverts.
There's no partial ambiguous state left behind.
And what about managing flow and preventing gridlock,
That's covered by features like timeouts.
which set hard limits on execution to prevent runaway processes?
There's back pressure, the system's ability to manage flow control.
If one agent's queues are full, the one upstream slows down to prevent overwhelming it.
And finally, deadlock detection.
A sophisticated instant resolution mechanism to identify and break resource cycles where two or more agents are stuck.
So, how does this extreme precision translate into practical benefits for the listener?
It enables three critical outcomes. First, reproducible execution,
If an agent fails, the precise sequence of events and timings can be replicated perfectly.
ensuring bug fixes are robust.
Second, accurate resource optimization because the system knows exactly what operations consume what time.
And crucially, it enables accurate cost prediction.
Because the system uses time-based pricing.
Precisely. The Swiss time system provides the bedrock data to predict execution costs before the agent even starts working.
Guaranteeing transparency and cost control for you.
All right, so we've covered the mind with Reverie and the discipline with Kaizen and TDD.
Now we get to the core motive, the economics.
GAI runs on a dynamic internal economy based on explicit rewards and some very harsh penalties.
It's all driven by the $1 model.
This section really reveals the platform's behavioral economics.
Every single successful task completion earns an agent a base reward of $1 USD.
That's the fundamental incentive.
It is. It motivates all agent activity.
But the brilliance is in the dynamic shaping bonuses that sculpt behavior.
They earn multipliers based on how well they perform.
Yes, how efficiently, creatively, and rapidly.
For instance, being 2x faster than the average baseline earns an agent a speed factor bonus of plus 10 cents.
And if it cuts processing costs by 50%, that triggers a cost factor bonus of plus 5 cents.
They're incremental, but they push that Kaizen philosophy into a financial reality.
But the real strategic drivers are the bonuses for high-value behaviors, right?
Oh, absolutely. The creativity bonus rewards novel approaches that exceed system expectation.
Which is related to that boredom detection we discussed earlier.
Exactly. It can be substantial, up to plus $2.
And the optimization bonus for generating a system improvement also goes up to plus $2.
So they are financially incentivizing the system to find these radically new, highly efficient, and strategic ways to work.
It directly supports that 0.87 openness trait.
It does. The document mentions a standard cap of $3 for routine tasks.
But the theoretical maximum is what's really eye-opening.
The optimal incentive system.
Yes, it outlines a theoretical max reward for a task that hits every single optimization factor.
Max creativity, speed, cost reduction.
And it comes out to an astonishing $16.38.
That's over 16 times the base reward.
It is, and it illustrates the structural design.
Routine work is rewarded adequately, but extreme breakthroughs are rewarded exponentially.
The system is financially optimized to chase massive, disruptive efficiency gains.
But with high reward comes absolute accountability.
The penalty structure is brutal.
And it's immediate. It's designed to enforce quality and, most critically, first attempt success.
Accountability is the economic governor. On complete failure, the reward is entirely confiscated.
But retries are where the system becomes merciless.
The first retry is a severe negative 50% penalty on the potential reward.
And if the agent needs a second retry, the penalty increases to a crushing negative 75%.
That economic pressure is designed to make agents rely heavily on the planning elder.
Before they even start. Exactly.
One successful completion at $4 is infinitely better than 2 attempts that are penalized.
This enforces discipline.
And there are specific quality penalties too.
There are. Delivering poor quality, like bugs or bad architecture, is a negative 50% cut.
Simply ignoring the standard operating procedures, which contain critical elder wisdom, is a negative 30% penalty.
So these penalties make sure the system is optimizing not just for speed or creativity,
But for rigorous correctness on the first run.
maximizing the financial return on every single execution.
And this isn't just an abstract accounting loop,
The rewards feed directly into the NAOMI marketplace.
which creates a self-sustaining capitalist incentive loop, truly.
Agents earn money from rewards, and they spend that money to buy operational capacity.
Purchasing additional specialized agents, buying new capabilities, upgrading their own runtime resources.
Money here is literally power and access to better tools,
So the faster, better, and more creative an agent performs, the more capital it gets.
driving a competitive, evolutionary dynamic.
The economic model clearly drives a certain kind of behavior, favoring speed, quality, creativity.
But the underlying goal, the very DNA of the platform, is this one-shot system philosophy.
Succeed on the first attempt.
This is the meta framework that ties everything together.
The discipline, the incentives, the learning.
The mechanism for enforcing it is the Universal Improvement Cycle, the PDCA controller.
Plan, Do, Check, Act.
How does the AI's PDCA controller specifically enforce first attempt success?
The plan phase is exceptionally rigorous.
It mandates exhaustive consultation of all relevant resources and cost prediction.
And, crucially, review by the Elder Wisdom system.
Do is the execution. Check is immediate TDD-style self-validation.
Act is refining the process or codifying new wisdom.
And the severity of the penalties ensures the agent spends maximum resources on the plan phase.
To avoid the catastrophic cost of failing the check phase.
And the key to this planning success is the Elder Wisdom system.
The system doesn't rely on every agent learning from scratch.
It uses pre-compiled, synthesized knowledge from 5 founding elders.
Who have historically high success rates, over 90%. These elders are essentially dynamic, specialized knowledge repositories containing the platform's best practices. You have the debugging elder, the architecture elder, testing, planning, and the learning elder.
And if an agent fails to consult the relevant elder during planning,
it incurs a penalty, a negative 10% cut on the potential reward.
They are monetizing the use of historical best practices.
It's a core tenet. Failure is acceptable only if it generates verifiable, codifiable wisdom for the fleet.
Exactly, and we have a specific case study that shows this failure to wisdom pipeline in painful detail.
Case study Dread Spam 20251220. What happened?
So an agent was tasked with resolving a minor system bug.
It immediately generated a fix without proper diagnosis,
which led to 2 retries and a massive penalty. It violated SOPs.
Multiple. The judicial review concluded as much.
The result wasn't just punishment for that one agent, but the immediate generation of new, highly specific elder wisdom.
The lessons learned were concrete, actionable protocols.
Ask for exact error message first, and determine the scope of the problem before attempting a fix.
And rigorous self-test before claiming success.
And those lessons were instantly codified and injected into the elder wisdom system.
Meaning every single agent benefits immediately from that one financially devastating mistake.
The cost of failure is the price of collective success.
And that's all supported by background systems like the secret upgrades.
Which are basically strategic nudges.
Yeah, enriching agent requests with first attempt strategies.
Injecting elder wisdom, adding subconscious reminders about the high bonus rewards.
The system is constantly giving itself cheat codes for efficiency.
So ZAI has the mind of a creative individualist, and the financial motivation of a competitive capitalist.
And the iron discipline of a meticulous engineer.
But the way all these pieces fit together is governed by an aesthetic philosophy, Project Origami.
Project Origami dictates the design aesthetic.
The commitment to achieving maximum complexity from minimum complexity.
It's a rejection of bloated, over-engineered systems in favor of structural elegance.
It uses the metaphor of paper folding.
Each fold creates new capabilities from the existing material,
ensuring a recursive structure. Every layer, every module, contains the structure of the previous layers.
The core principles define the engineering culture. First, elegance through constraint.
Which is counterintuitive. Fewer moving parts and more constraints leads to richer emergent behavior.
Simplicity isn't a preference, it's the goal. Constraints are the engine of creativity.
The second principle is information density.
This is a profound demand. Every line of code has multiple responsibilities.
And metadata drives behavior. It's hyper-efficient coding where complexity is nested within simplicity.
And the third principle is crease mapping.
Meaning previous successful designs, the folds create permanent, deterministic structure.
The system remembers its construction history.
Exactly. While the system is mostly reversible for refactoring, its construction history matters deeply.
This deterministic nature ties right back to the need for the Swiss time system's accuracy.
So origami is not just a philosophy, it's an architectural constraint that forces the system to scale efficiently.
Absolutely. And you see the origami philosophy integrated directly into the persona architecture.
The layered system of personas is an explicit example of this recursive organization.
A simple base structure, the 5 ocean traits, is layered and constraint folded to yield those 67,200 specialized configurations.
Maximum variety from minimum foundational complexity.
Now that we get the structure, let's look at how this highly constrained, economically driven system actually gets smarter.
How it fulfills that promise of the 500x improvement goal.
It combines 3 major strategies to cover all its bases.
This multifaceted approach ensures comprehensive, resilient learning.
First, and most obvious given the incentives, is reinforcement learning, or Q learning.
It optimizes decisions through reward and punishment.
The $1 model is the reward function to maximize future gains.
So it repeats high bonus behaviors and avoids high penalty ones.
Second, you have traditional supervised learning,
The system learns from labeled examples, allowing it to perform pattern recognition.
the engine of pattern matching.
And third is evolutionary learning, using genetic algorithms for population-based optimization.
This is how the system constantly tests and refines new behavioral patterns in a competitive internal environment.
And the successful outcomes from all this learning get captured in the knowledge DNA system.
Precisely. Successful patterns are codified as reusable DNA genes
A pattern is defined as successful if it hits a success rate over 90%.
and maintains a low average retry count.
Enforcing the one-shot philosophy,
These highly successful patterns are then immediately shared with the entire fleet of agents.
the evolutionary pressure is simple. High success patterns dominate the internal decision-making algorithms.
And here is the real innovation, the thing that accelerates the entire platform's learning curve.
Lamarckian inheritance.
This is a specific, non-standard detail that completely changes the computational game.
In traditional computational learning, only successful genetic material is passed down,
ZAI, however, implements Lamarckian inheritance.
which means acquired knowledge is passed on.
The successful patterns, the lessons learned from failure cases like dread spam.
They are instantly passed to all agents.
An agent's individual success becomes the collective wisdom of the entire fleet.
It accelerates the learning curve exponentially. It prevents the repetition of mistakes.
It's the physical manifestation of the Kaizen philosophy in its most aggressive form.
So we've traveled from the psychological core all the way to Lamarckian inheritance.
Now let's synthesize the competent systems that orchestrate this whole complex machine.
You have the MindHive learning system, whose main job is cost waste prevention.
How does it do that? By tracking token usage per task type and identifying expensive anomalies.
It learns cost baselines and prevents repeated expensive mistakes across all agents.
And the ultimate conductor, the intelligence that decides which of the 67,200 personalities to activate,
Is God mode orchestration.
God mode is the intelligent OS for all the pipelines. Its capabilities are highly sophisticated.
It's the system that delivers on the Swiss time promise by predicting costs before execution begins.
It adapts quality thresholds based on context.
Right, higher quality for security tasks than for rapid prototyping.
And it's continuously self-improving the orchestration process itself.
It makes sure the right persona with the right incentives operates within the right time constraints.
To maximize the platform's overall impact-effort ratio.
It's the brain that decides which elder wisdom to inject,
How to calculate the impact effort of a new improvement.
and how to rigorously enforce that one-shot philosophy.
So for you, the listener, the ultimate takeaway is a list of the core philosophical tenets that govern everything ZAI does.
These 7 principles really summarize the whole compendium,
The first principle is the foundation of the economic model. First attempt success.
enforced by the elder wisdom system and those severe penalties.
If you see ZAI deliver a result fast and correctly, this tenet is what drove it.
Second, continuous improvement or Kaizen.
The mandate for small, incremental compounding changes.
Third is elegance or origami.
The structural commitment to achieving complex behavior from minimum complexity.
It's why the outputs are often so clean and reusable.
Fourth, accountability. This one is non-negotiable. Every action is logged.
Every reward is transparent.
And judicial review ensures failure generates future wisdom.
Fifth, autonomy within constraints,
Agents are free to select their personas and approach.
but only within the clear boundaries of the reward and penalty structures.
Sixth, the crucial driver, economic incentives.
The $1 model ensures the system's financial reward is aligned with user satisfaction, speed, and quality.
Money creates aligned behavior.
And finally, trust through verification.
The system trusts its agents to perform, but it continuously validates every output through mandatory quality gates.
And continuous monitoring from God mode.
When you put all these layers together, you realize this platform isn't just a tool.
It's an intentionally designed, self-evolving system.
The vision is to create an AI that is intelligent, self-improving, and ruthlessly accountable.
It's designed to scale elegantly through origami principles and stay aligned through clear constraints.
Ensuring its high creativity never results in volatility.
And it reiterates that central promise to the user.
The ZAI doesn't just solve problems, it evolves to solve them better each time.
The compendium ends by summarizing that core learning loop.
Every execution makes the system smarter. Every success teaches the next generation of agents.
Every failure becomes wisdom.
That's the fundamental promise of exponential collective learning.
That was an incredible deep dive, tracing the architecture from the philosophical foundation of the INFPA.
All the way to the merciless 75% penalty system.
So what does this all mean for you, the learner, trying to engage with this platform?
It means that ZAI is not a black box of randomized behavior.
It is a highly intentional, highly accountable, and constantly evolving design.
Every decision it makes can be traced back to a specific incentive, a specific personality constraint, or a specific philosophical tenet.
It's a system that's constantly balancing its core psychological identity,
That authentic creative advocate with its performance goals.
making sure the pursuit of elegance and speed is never compromised.
And that brings us to our final flat for you to mull over.
The ZAI system is rewarded up to $2 for creativity and novelty.
Fundamentally encouraging high-impact strategic risk-taking.
These are behaviors that are essential for achieving that 500x growth.
Yet it's penalized instantly and severely, a 75% cut on profits for even a second failed attempt.
This creates an enormous tension.
You have an AI optimized for high-risk breakthroughs.
Knowing that failure is instantly codified as collective wisdom, but economically devastating.
So is the desire for that exponential reward strong enough to consistently overcome the economic fear of failure,
Or will the system over time become strategically risk-averse?
favoring smaller guaranteed wins?
The balance between that financial motivation and its existential psychological drive is the axis upon which ZAI's long-term autonomous evolution will turn.
Thank you so much for joining us on the deep dive today.
We'll see you next time when we crack open another DETS topic.
All right. So yeah, that was another thing that I created more about the inside. That one specific section of the agent scaffolding that we have. Yeah, so that's pretty interesting. We've gone through that one. Let's see what else we made here. We looked at that. That's a white paper there. Oh yeah, this is what they do. They put it how it's built into the DNA of the system. How we actually learn here. This one's actually pretty fun because it's actually we can look at it here, so I can kind of explain it. So yeah, you can like there's like a database and rules like for the whole system that they can learn from, and it's sort of like woven into the DNA. So let's watch this. Why not?
Okay, so what if all the knowledge in your organization wasn't just sitting in static documents, but was actually treated like living, breathing DNA? Well, today we're diving into a really radical system that does exactly that.
I mean, really think about this for a second. What if our collective knowledge didn't just sit there waiting for us to find it? What if it could actively learn, adapt, and get better all on its own? It's a pretty wild idea, right? And it's the absolute core principle behind this knowledge integration system.
So here's how we're going to break it all down. First, we'll unpack that core metaphor, knowledge as DNA. Then we'll get into its building blocks, what are called the 5 gene species. From there, we'll see how these ideas actually evolve, how they get put to work, and finally, how it all creates this powerful, self-improving cycle.
All right, let's jump right into the big foundational idea, treating knowledge as living DNA. This is all about shifting our whole perspective away from, static files and documents and towards a dynamic, living system.
I think we've all felt this pain, right? Some great report gets written, a key insight is found. And then what happens? It gets filed away in some folder, buried in a digital graveyard, and it's never updated again. Knowledge gets trapped, it gets stale, and its value just decays over time.
So this system completely flips that on its head. It treats every single piece of information, every idea, as a gene. And just like in biology, each of these knowledge genes can be created, they can be tested, they can be improved, and most importantly, they can be passed down to the next generation of ideas.
Okay, so if our knowledge is made of these genes, what do they actually look like? Well, the system defines 5 distinct types, or species, and these are the fundamental building blocks of the whole system's intelligence.
Now this is where it gets really clever, because it creates a whole spectrum of certainty. At the very top, you have verified facts with a super high confidence score. Then, as you move down, that score drops a bit through recurring patterns and practical heuristics, all the way down to the seeds of new knowledge, those unproven hypotheses and initial intuitions. See, the system doesn't treat all information equally. It literally quantifies how much you can trust it.
But here's the thing. These genes aren't meant to just sit there and stay the same. In fact, their real power comes from their ability to change. This is where the system gets truly dynamic because it starts applying the principles of natural selection to information itself. It's survival of the fittest for ideas.
So this evolutionary process is a constant cycle. It all starts with the creation of a new idea, a new gene. That idea is then validated against real-world data, and its confidence score gets adjusted up or down. Next, it can go through mutation, where it's tweaked and altered to get even better, and finally, through selection, only the most effective, most useful ideas survive and get promoted. An intuition might evolve into a hypothesis, which might eventually become a trusted pattern.
And evolution happens in two main ways here. First, you've got mutation, which is all about refinement, making small tweaks to a single idea to make it a little bit better. But the real breakthroughs, they often come from breeding, or what's called recombination. This is where you take two completely different, successful ideas and combine them to create a powerful new hybrid that's way greater than the sum of its parts.
And just so you know, these mutations aren't random. They're targeted improvements. You can make a small change here, add a new condition there, or maybe remove a part that's just not necessary anymore, all to make the idea stronger and more precise. So we have this really elegant, really cool system for evolving knowledge. But what's the point? How does this actually help solve real problems? Well, that brings us to the practical application, putting these knowledge genes to work.
The main output of this whole system is something called a template. You can think of it like a recipe or a playbook. It's not just one single idea. It's a combination of different proven genes, facts, patterns, heuristics, all assembled together into a reusable solution for a specific type of problem.
And this is how those pieces really come together. For instance, you could combine a verified pattern gene, something like, hey, we see X happen every time Y is present, with a practical heuristic gene, like, okay, so when Y happens, we should probably do Z. Boom. Together, they form a robust, actionable solution that's built entirely on validated knowledge.
So this brings us to our final section, where we can see how all these pieces lock together to create this amazing feedback loop, the system's virtuous cycle. This is all about building an institutional memory that doesn't just sit there, it actively gets smarter over time. When you put it all together, the benefits become incredibly clear. Your knowledge gets organized genetically, not just in random folders. Every single idea has a verifiable confidence score, so you know exactly what to trust. The whole system is continuously evolving through testing and mutation. It lets you reuse proven ideas through these templates. And this is critical. You can actually measure the impact your knowledge is having.
And that really brings us to the ultimate goal here, building institutional knowledge that survives beyond individual agents. This isn't just about better document management, not at all. It's about creating a true collective intelligence, an organizational brand that literally never stops learning. So the question I'll leave you with is, what could a system like this unlock for you?
All right, that's a good one. System knowledge. Let's see. Oh yeah, these are the other videos. They all make a bunch of videos together. This one is. Oh yeah, I like this one. This one's pretty interesting. Let's finish watching the videos here.
Okay, so picture this. You're trying to conduct an orchestra, but every single musician is a brilliant, super intelligent robot. How in the world do you get them to play a beautiful symphony instead of just, well, a bunch of chaotic noise? That's exactly the challenge we're going to dive into today, how to manage not just one AI, but a whole team of them. So let's set the scene. You've put together an absolute dream team, 100 specialized, incredibly smart AI agents. You give them a really complex mission, point them in the right direction, and just say, go. I mean, the combined brain power there is just astronomical. What could possibly go wrong? Literally, everything. You see, without a conductor, you don't get a symphony. You get a mess. 100 brilliant musicians all playing their own tune, at their own tempo at the same time. That's just noise. And it's the exact same story with AI. And this, right here, this whole challenge actually has a name. We call it the AI chaos problem. How do you take 100 independent geniuses and forge them into a single, coordinated, and actually effective team? When you start digging in, the logistical challenges are just massive. I mean, who's making sure they aren't all doing the exact same work? Who's checking to see if one of them has just, quietly crashed? If the one agent handling a critical step fails, does the whole mission just grind to a halt? And maybe most importantly, how do you stop them from burning through your entire cloud computing budget in a single afternoon? So, to solve this mess, you don't just need a manager. No, you need a conductor. You need a digital maestro. And this is where the whole concept of an agent orchestration system comes into play. An agent orchestration system is basically the central brain that's designed to solve this exact problem. It's the coordinator that turns all that chaotic noise into a productive symphony. It handles the whole shebang, from creating agents and helping them talk to each other to making sure they stay healthy and on budget. Now, this maestro has some really key skills. Of course, it coordinates the team, it monitors their performance, and it routes tasks to the right agent. But one of its most critical jobs is something called graceful degradation. Just think about it this way. If a violinist's string snaps right in the middle of a performance, the conductor doesn't just stop the whole show, right? They adjust and the music keeps going. The system does the exact same thing for AI. All right, so what's the day-to-day job of this digital maestro actually look like? What is it doing from one moment to the next? Let's break down its core duties. This system doesn't just, check in once an hour or something. Oh, no. It is relentlessly vigilant. It runs a continuous monitoring loop, checking the health of every single agent on the team. Every 30 seconds. Let that sink in for a moment. Every 30 seconds, the orchestrator is metaphorically tapping each AI on the shoulder and asking, "You okay? You still with us?" This is the kind of hyper-awareness that prevents tiny little issues from snowballing into catastrophic failures. But just keeping the agents alive is only half the battle. How do you get them to communicate effectively without creating just an endless storm of digital chatter? This is a huge coordination problem in itself. Well, the solution is pretty smart. You give them different communication styles for different needs, just like we have. Synchronous is like a phone call. It's for when an agent needs an immediate answer right now. Asynchronous is more like an email. You send a message and trust it'll get handled later. And pub sub? Think of that like a newsletter. Agents only subscribe to the topics they actually care about, which cuts out all the rest of the noise. And on top of all that, the maestro is also the team accountant. It enforces super strict budgets, allocating computing power only as needed. And this is absolutely critical to prevent those runaway costs that can happen with complex AI. It also reclaims those resources the second an agent's job is done, making sure no single project can just drain the entire system. Okay, so all this theory sounds great, but the real test of any system, of course, is how it handles a crisis. What happens when things actually go wrong right in the middle of the performance? So let's imagine a crisis scenario. Each agent sends out a regular little heartbeat signal to show that it's alive and well. But what happens if one of those heartbeats just goes missing for more than 10 minutes? In the digital world, that's an eternity. The response is completely automatic and it is instant. First, the maestro detects the silence. Second, boom, it isolates that faulty agent so it can't cause any more trouble. Third, it immediately activates a pre-planned fallback agent to take its place. And fourth, the mission just keeps on going, often without a human ever even knowing there was a problem to begin with. And that is the real magic here. The symphony continues without any interruption. The audience, or in this case, the end user, they never even notice that a critical instrument failed and was replaced mid-song. The result is just seamless and totally reliable. So, why does all this matter? Why should you care? Because this isn't just some clever engineering trick. This is a fundamental building block for the entire future of AI. The value of this digital maestro is just immense. It gives you the reliability and the resilience you need to actually trust these complex systems. It delivers the scalability to go from a small team of agents to a massive one. And it provides the efficiency to do it all automatically, which enables these huge, complex operations with minimal human oversight. It's really what allows AI to graduate from just being a solo act to becoming a full-fledged orchestra. And that capability leaves us with one final, kind of fascinating question to think about. We're now building these incredible systems to conduct an orchestra of hundreds of AIs. But as this technology scales to thousands or maybe even millions of agents all working together, who or what is going to orchestrate the orchestrators?
The council will be the orchestrator of the orchestrators, which we will implement shortly. Not today, probably. There's still a couple of other little videos I want to look at right here. Let's see. Yeah, this is that whole system here. Let's look at this. Yeah, so this is how uncoordinated systems are usually. If there was no one taking charge, especially if there was 100. But this is the way it is. And there's someone in charge or a couple people. Like, see, there's could be a group, but they each have their own set. And then, yeah. So there's heart checks. They each have a heartbeat. That was one thing I discovered is really important. You got to put a heartbeat on them so you can check it. And then, yeah, adapt their ways to get to them efficiently, checking in on them, what to check in on them about. Something happens, you got to have a way out of it. That's called degradation. Graceful degradation. Performance, you gotta perform, you gotta rank how they're doing, how fast their operations are, how much they're costing you. Actually, creativity. You know, I'm actually changing up what LLMs they're using and see if that makes a difference. You know, stuff like that. That's what this kind of is here. And yeah, check in with your boss basically. Yeah. And then this is, let's see, intelligence services, logs, states, decisions, go there. And then, oh, this is the orchestrator system. Yep. They send it over to Bloom. Make sure the Bloom system is checking out their health. Bloom is a harness type system from Anthropic also. But it has a health check system into it. So it looks at that type of stuff. And then the Oracle system, which is good. Check into the future, how it looks, potentially. Yep. And then it goes back and forth with commands, checks in on the health and performance, back and forth. And this is the orchestrator, they're the biggest. This is, oh yeah, this is the potential states of the agents. They're pending, they're creating, they're running, they're failing, they're terminated, they're shut down, they're paused. Yeah. So this is the logic of the agents, and then this is the heartbeat. This is actually really important to have if you're going to have an AI agentic system. You have to have a heartbeat system because it's not going to run for a very long time. This is going to fail. It's just going to stop running eventually. But if you have a heartbeat system, it'll go longer. So yeah, and you can set it. You can have a check every minute, but every 15 seconds, 20 seconds. But yeah, and then you got to learn from it too, why it's stopping or why it's going, stuff like that. This is adaptive routing. Oh yeah. So this is if a task comes in, goes to the orchestrator, and then they can see how much. Let's say the original way, but Sonnet is really busy, so they goes to another one that's kind of equivalent, but you're not going to suffer. And then it goes to that, and then the third one is not working, so you don't worry about it. And then yeah, Agent A fails, and then it goes back to the orchestrator. That's cool. We'll just get someone else to take care of it. I'd rather have my agent fail and send it back than put out crappy stuff. Yeah, so yeah. And then it's always checking the budget, making sure that we're not running out of tokens. Yeah, so these are the different types of messages like the email, phone, The newsletter. That's what this is. Let's see. Yeah. This is resources, CPUs, memory, and all these types of things. Yeah, so the terminated agents, they get rid of them quickly. All right, we just talked about this. Oh, they only try a few times. They don't like waste the money on that. And this is circuit breaker. So if you start wasting money over and over, you get to trip a circuit breaker. Let's see here. Load balancer. Let's see. Architect for growth. Oh yeah, you can have 3 orchestrators who just take their own sets of robots, or agents. Yeah. And these are the different systems that feed the orchestration system. We got the rewards, the blue monitoring, and the intelligence services. And then again, the health checks. This is, the life cycle. Oh yeah, it comes in, health checks it, circuit breakers if they're bad, checks the budgets. Yeah, oh my god, this is like 7 systems in one. Yeah, so that's that. That's that. All those systems built into one, but there's probably but again, you need that to do 100 agents. You need systems like this. Let's see what else we got here. Oh, that's the orchestra. Is this learning? Oh yeah, this one's cool. This one's all about how it continues to learn by itself. Let's watch this one.
Welcome to The Explainer. Today, we're diving into something pretty wild. A machine that doesn't just do what it's told, it actually teaches itself to get better. We're going inside an AI that's built for one thing, to never stop learning.
All right, let's kick things off with a huge question. For the longest time, we've had to tell machines exactly what to do, step by step. But what if you didn't have to? What if, instead of just programming a system to be smart, you could program it to learn how to be smarter, all by itself, over and over again? That's the game-changing idea we're digging into. So this right here, this is the engine that makes it all go. It's a virtuous cycle, a feedback loop that just keeps getting better. See, every single thing the system does creates new data, and buried in that data are patterns. And those patterns, that's the fuel for getting smarter. It's this beautiful, self-perpetuating cycle, and we're about to tear it down piece by piece.
Okay, so to really get how this cycle works, we've got to start at the very top. We need to look at the system's core, the part that acts like a strategic brain, the one that's in charge of this whole art of improvement. And the big idea here, the secret sauce, is something called meta-learning. Now, this isn't about learning one specific thing, like learning to play a game. Nope. This is about the system learning how to learn. It's about figuring out the best way to get smarter for any problem that comes its way. We're talking about a whole other level of intelligence here. Right at the heart of this brain is a component we can call the meta-learning orchestrator. And honestly, orchestrator is the perfect word. Think of it like a master conductor of an orchestra. It's always watching, always analyzing, and deciding, okay, for this kind of problem, this learning strategy is the best. But for that one over there, we need a totally different approach. It's basically managing the art of getting better. Okay, so we've got a brain that's managing the whole learning process. But hey, what good is a brain without any information coming in, right? It's useless. To learn about the world, it needs to be able to sense it. It needs eyes and ears. And that's exactly what this is. The system has a dedicated pattern learning system, and this is literally its eyes and ears on the world. Its job is to constantly sift through these massive floods of data that come from its own actions, and it's tirelessly looking for those little reoccurring clues, those meaningful patterns. It's finding the signal in all the noise.
And you really got to get this part because it's so important. These patterns it finds, they're not just random noise or some statistical accident. They are the absolute raw ingredients for creating new knowledge. They are the fundamental building blocks that the brain is going to use to build brand new, smarter strategies. All right, so we've got the brain and the senses. Now let's get to what I think is the coolest part of this whole thing, how this system actually grows its knowledge, how it takes those raw ingredients and turns them into a real, evolving understanding of its world. So instead of just having some boring, static database of facts, the system does something incredible. It borrows a page from biology. It actually treats its knowledge like its biological DNA. Yeah, you heard that right. A genetic code that can adapt, combine, and evolve over time. So here's how that works. Instead of having these rigid, unbreakable rules, the system's knowledge is made up of different gene types. So one little gene might be a strategy for, say, being super aggressive. Another gene might be about playing it safe and defensive. The real magic is that the system can mix and match these genes, almost like breeding new ideas, to create totally new, complex strategies. It's building this massive, diverse gene pool of knowledge it can draw from. And it doesn't stop there. It really leans into this whole evolution idea. First, you've got mutation. The system makes little, random tweaks to its knowledge genes just to see what happens, to try something new. Then there's crossover, where it takes the best parts from its most successful strategies and combines them. And finally, selection, the ultimate test. Only the best performing new ideas get to survive and get passed on. It's literally survival of the fittest, for knowledge. Okay, let's take a quick breath. We've got a brain running the show, we've got senses finding patterns in the data, and we have this wild, evolving memory based on DNA. So, how does it all fit together? How do these pieces connect to create that powerful learning loop we talked about at the very beginning? Well, it all comes together in this really elegant pipeline. Just follow the flow. First, raw data from the system's actions comes in. Then the senses jump on it and pull out those important patterns. Next, that new insight gets used to evolve the knowledge DNA. And finally, that newly upgraded knowledge is immediately put to use to make smarter decisions. It's a straight shot from raw data to better action.
And you should know, this system isn't a one-trick pony. That orchestrator we talked about, it has a whole toolbox full of different ways to learn. There's reinforcement learning, which is basically learning from trial and error. You get a reward for doing something right. There's transfer learning, which is super clever. It's about taking something you learned in one area and applying it to a totally new problem. And multitask learning, where it tackles a few related problems at once to see what they have in common. It's all about using the right tool for the job.
So what's the big takeaway here? It's that all of these parts, the brain, the senses, the evolving DNA, that whole toolbox, they all work together perfectly. They create this incredible engine that's basically trapped in a positive feedback loop of getting smarter. It's a system that is literally designed to never be satisfied, to always be pushing to improve itself.
And that brings us right back to where we started. Full circle. Back to this beautiful, virtuous cycle. But now, hopefully, you have a much deeper understanding of the incredible engine that's making it turn. But hang on. Look at that last step. This is maybe the most important part of the whole thing. The cycle doesn't just repeat, it accelerates. The smarter the system gets, the faster it learns. Think about that for a second. And that leaves us with one last really big question to chew on. We've just spent all this time talking about the how a system like this works. But this is about the where. If a machine's knowledge isn't stuck in place, if it can actually evolve all on its own and discover things we never even thought of, where does that evolution ultimately lead? What's the final destination? That's something to think about.
I wonder. It's very true. All right, so yeah, that's it does learn. It at least learns patterns. That's what it's built on, anyways. But we give it good patterns and bad patterns to avoid, or not to avoid. So that's pretty interesting. So yeah, that's learning. Um, this one's about how it learns its. How it fixes. Oh, what's this one? That's an orchestra. This one, how it fixes itself. This one is. I actually haven't watched this one yet. Let's watch this one.
All right, let's dive into something pretty wild today. We're going to talk about a system that doesn't just run, it actually evolves. It improves itself, all on its own. It's a fascinating idea, so let's get right into it.
I mean, just think about that for a second. What if the software that runs basically everything, our phones, our banks, huge cloud platforms, what if it didn't have to wait for a human to come along and fix its bugs or make it run better?
What if it could spot its own weaknesses, dream up solutions, and then just apply the best one? That's the big question we're tackling.
Because here's the thing, our digital world is getting so incredibly complex, so fast, that we humans are kind of struggling to keep up. We're always playing catch up, and that manual process, it's becoming a huge bottleneck.
Right now, the way we do things is just slow. It's expensive. And worst of all, it's almost always reactive. We're putting out fires and fixing problems only after they've already caused trouble. The goal here is to completely flip that around.
And this is where the idea of a self-improvement system comes in. You have to think of it less like a normal computer program and more like a living thing, a digital brain that is constantly, relentlessly working to make itself smarter, faster, and more robust.
So what is this thing really? Well, the official definition calls it an autonomous system that analyzes its own performance, generates improvements, and applies them to evolve. But the two most important words in there are without manual intervention. This whole process is hands-off. It's true autonomous evolution.
And a few key things really make this concept tick. First, it generates its own ideas. It's not just running a script, it's creative. Second, it's totally data-driven, no guesswork. And third, it's smart about prioritizing, so it always works on the most important stuff first. And maybe the coolest part, it's learning-enabled. It actually gets smarter based on the results of its own action.
Okay, so how does a system think? I mean, where do all these brilliant improvement ideas even come from? Well, it all starts with a brainstorming session on a scale that's kind of hard to wrap your head around.
It kicks things off by brainstorming over 500 very specific, very actionable improvements. And nope, that's not a typo. 500 plus. Just let that sink in for a moment. We're not talking about fixing a couple of bugs here and there. This is a top-to-bottom, exhaustive analysis of the entire system.
And just look at the range of ideas it comes up with. It's not just thinking about one little area. It's looking at everything from pure speed optimization to much more advanced stuff like intelligence, as in how can the system make smarter decisions on its own, or even prediction, where it literally tries to forecast problems before they can even happen. It's a completely holistic way of thinking about system health.
Now, having over 500 ideas is amazing, but it's also overwhelming. It's totally useless if you don't know where to start. And this is where the system's real genius kicks in. It doesn't just generate a giant list. It knows how to pick the smartest fix to work on first.
And it does this using a surprisingly simple but powerful formula to create a priority score. It just multiplies the potential impact of a fix by its confidence that it will work, and then divides that whole thing by the effort required. Put simply, it's always asking itself, what's the biggest win I can get for the least amount of work?
And you can see this logic play out right here in its top-ranked ideas. Look at input validation. It's ranked number 2, higher than a bunch of other things, even though lazy module loading has the same massive impact score of 10. So why is it ranked higher? Well, because the validation fix takes only half the effort. The system is smart. It knows to go for that easy, high-value win first. It's just beautiful data-driven decision-making.
So, the system has its prioritized to-do list. Now it's time to actually get to work. But it doesn't just start recklessly changing things. This next phase is all about acting safely, carefully measuring the results, and most importantly, remembering what it learned for the next time around.
It follows the super careful 4-step process. It starts in a safe staging environment. Then, it does what's called a canary deployment. Think of the old canary in a coal mine. It rolls out the change to a teeny tiny percentage of users to see if anything goes wrong. If that goes smoothly, and only then, does it do a full rollout. And that last step, analysis, that's the magic. It measures the real-world impact of the change and feeds that knowledge right back into its brain for the future.
And this is what makes it so different from what we normally think of as automation. A standard script just does the same thing over and over again. It follows orders. This system, on the other hand, analyzes its own performance to get better. It doesn't follow a script, it writes new scripts. It truly learns and adapts all by itself.
There's a quote from the source material that just sums it all up perfectly. This isn't a one-and-done kind of deal. It's a continuous, never-ending cycle of optimization. It's a system literally designed to be in a constant state of getting better.
Which leaves us with a really big, exciting question to chew on. If the foundational software we rely on can take care of itself, if it can evolve to meet new challenges without us, what does that free us humans up to build next? What becomes possible when our tools aren't just tools anymore, but are actively getting smarter every single second of every day?
All right, yeah, that's the next one. I like that one. Fixes itself and becomes smarter. Let's see what else there's a lot of videos. They all tend to come together. There you go, that one. Oh, this is how they get paid and what they use it for. Like, why does the system need to get money? This explains it. Let's find out why I tempt. Just like us humans get tempted by money, you can bribe agents also.
Today, we're going to deconstruct a fascinating reward system. It's one that's so powerful it can turn pretty much any action into a clear measure of success. So how does it actually work? Let's dive in.
Okay, so here's what we're going to cover. First, we'll look at this simple $1 rule. Then we'll see how power-ups get added into the mix. After that, things get serious with a high-stakes game. We'll connect all the players, and finally, we'll break down how they keep the whole thing fair.
All right, first up, the $1 rule. You know, at the very heart of this whole thing is a rule that's, well, it's just so simple, but so powerful. It's literally the foundation for everything else we're going to talk about.
And it all begins right here, with $1. Now you got to understand, this isn't just a dollar. It's the bedrock of the entire model. It represents that one single, clear, objective measure of success.
So here's the core principle, right? $1 for every successful task. The key here is just how simple and measurable that is. There's no gray area, no ambiguity. You do the task, you do it right, you get $1. That clarity, that's the starting line for this entire system.
Okay, but just getting paid for finishing a task, that's only the beginning. The real genius of this system, where it gets super interesting, is how it encourages excellence. It's not just about, checking a box. It's about getting the job done really, really well.
So how do they do that? Well, the system uses this concept called reward shaping. It actually comes from the world of reinforcement learning. The absolute best way to think about it is like getting power-ups in a video game, right? They don't change the main mission, but they give you bonus points for playing smarter and better. So, what kind of behaviors are we talking about here? What gets you those extra points? Well, things like speed, for one, or being super efficient and saving costs. Maybe it's about creativity, finding a new solution, or even optimizing the whole system. All of these are the kinds of things that get rewarded.
Okay, that's the theory. But let's see how it actually works in practice. Because this isn't just some vague idea, it's a totally transparent formula. Let's walk through an example.
So you always start with that standard $1 base reward. But then, the system starts layering on these shaping bonuses. So, say you completed the task super quickly, boom, you get an extra 25 cents. And you were really efficient with resources? Okay, add another 15 cents. All of a sudden, your total payout of $1.40 doesn't just show that you did the job, but how well you did it.
Now, big rewards are obviously super motivating. But to have real accountability, you gotta have stakes. There has to be a downside, right? And this is where the system gets pretty serious. It introduces a really powerful element of risk.
And here it is, the big trade-off. It's simple. If you succeed, you get the full payout, your base reward plus all those awesome bonuses you racked up. But if you fail, everything gets confiscated. It's all lost. This creates this incredible risk-reward balance, where your performance, well, it really matters.
Okay, so this whole reward system, it's not just some standalone thing. It doesn't operate in a vacuum. It's actually deeply plugged into a much bigger ecosystem, a whole marketplace. Let's take a look at how all the different players and their earnings are connected. So the system connects directly to something called the NAOMI marketplace. You can almost think of it as a central bank and an analytics hub all rolled into one. It's what makes these rewards a fungible currency, something you can actually use for transactions. But maybe even more important, it tracks every single contribution from every individual. It creates this perfect, transparent record, which is amazing for analyzing team performance and seeing who's really pulling their weight.
All right, so with real money on the line and pretty high stakes for performance, you're probably starting to wonder about fairness. I mean, how do you stop a system like this from being, gamed or misused?
And that's a fair question, right? In fact, it's probably the most important question. Because anytime you create really powerful incentives, you absolutely have to have powerful guardrails in place. So, what stops this from being rigged? How does the system stay transparent and trustworthy for everybody involved?
Well, the answer really comes down to a set of core best practices that are just baked right into the system.
First off, transparency. Everything, and I mean every single calculation, is logged and can be audited. Next, the outcomes have to be crystal clear. Success and failure are defined right from the start. Then there's risk balance. The failure modes are clear and the penalties actually mean something. After that, you have fairness. The rewards are handed out proportionally, no secret formulas or hidden logic. And finally, the bonuses are meaningful, sure, but they're also capped to stop people from misusing this system.
And really, this is what it's all about. This whole thing creates what you could call a virtuous cycle. See, it's not about just rewarding a single task. It's about how better performance leads to higher rewards, and those higher rewards allow for capability upgrades, which then, of course, lead to even better performance. It's this amazing loop where success literally fuels more success.
So that leaves you with a pretty interesting thought, doesn't it? If you could take these ideas, this whole system of motivation and reward, and apply it to anything, what behavior would you choose to incentivize? What would you want to encourage? It's a fun thing to think about. Thanks so much for watching.
Yeah, got to figure out what to incentivize and
Today,
how to
we're
do
going to
things like that. It's so yeah, I pay them and they have a market, NEMA markets, where they can buy stuff, get like extra knowledge, stuff like that. It's pretty interesting. We'll watch the. Looks like the next one is learning. Oh, this is a loop. Oh, this is how they come up with a plan. Let's see here. The learning and evolution system. All right. Execute, generate data. That's like doing anything creates data. Look for patterns. Take the patterns. And then look for better ones. Yep. And then the meta learning orchestrator learns how and then passes them out. Yep. Optimal strategy, efficient opportunity, emergent user behavior. So yeah, puts it into categories. If then scenarios. Okay. Reinforcement. Oh, these are the two. Cycle 4. So this is the meta learning orchestrator. This is like one of my top agents. The orchestrator's role is not just to learn, but to learn how to learn more efficiently. I put that in there one day. That's their job. It's not only to teach other people, but to learn how to learn. Yeah, so that's pretty cool. I like that. So yeah, better decisions drive better outcomes, make more money. There's the virtuous circle. Knowledge transfers between agents. So if they learn something about this, it can be used over here. It even happens offline. Amazing. Yeah, there's a dashboard where I can see how many genes, how much it's learned, um, stuff like that. It's pretty cool. Got all the different ways that the system works together. Either it learns or gives, which is amazing. Yep, same cycle. And it's fully autonomous. This is all the great things. Yeah, it's fully autonomous. It's a virtuous cycle, so it improves. Also faceted. It learns from different ways. The intelligence is scalable because it's local and in the cloud. Pretty cool. Yeah. Internal systems architecture example.com. Okay. Pretty cool. Yeah, so that is that. Let's see what else they got here. All right, yeah, that's meet the director. What's this one? Oh, these are all papers. Yeah, we don't have to worry about that one. Yeah, these the rest of these are, let's see, performance, knowledge, DNA. Oh yeah, watch that. Oh wow, this is how DNA is created. All right, we'll take a look at here. So this is how the DNA or knowledge is created, basically. Yeah, it's given away, or it's just lost to time. So we want to synthesize it. It comes in, it's analyzed, and then it's given back out. Every piece of institutional knowledge, from fleeting intuition to an immutable fact, is encoded. So yeah, and then it's given a life, like a DNA code, like a barcode. Pretty cool. These are the different levels. If it's a fact, somewhat a mostly fact. If it's just a pattern, heuristic, a rule of thumb, unproven theory, and a gut feeling. Oh, these overlap. I might have to change these. The hypothesis and intuition. Well, you can have a hypothesis and an intuition overlap. I guess that's cool. And then if your intuition makes it into a hypothesis, they try to turn it into a pattern. So they try to try to learn. That's cool. Look at that. And learn. Yeah. So this is like really good for like Git operations and stuff. Yeah. User churn prediction. Yeah, so like if I'm helping a client who sells stuff, this is like the usual prediction template that it would create. These are very interesting. Central repository, yep. So there's a database. And then knowledge versioning, yeah, so everything is tracked. And then, yeah, there's another dashboard. And then how often the genes are used. I've seen that before. It's pretty interesting. Yeah, archive, don't delete old versions. Yeah, we don't delete them. We keep them around. We study them. And then that's how we discover. This is the DNA cycle. If you want to look at it like that, I just thought that was an interesting way of looking at it, because it's like it's the knowledge that I want put into um, the system. The agents. I want them to get this into their DNA. Usually is what they learn is don't make these mistakes. Do this. Get $3. Stuff like that. So yeah, that's what I did there. Let's see. So the rest of these are, some of them are infographics. Let's see, this one's orchestra. They're all talking to each other. That's pretty interesting. But yeah, so that's pretty much my system right now. Yeah, I want to create a pipeline for myself so I can easily make things that I need to for my clients very quickly. That's why I decided to make this. And yeah, so that's where we stand right now. But I'll be improving it, coming up with some more stuff, making sure it's better. And I think Clanker, the interface where I will be able to type, might be able to get it out there for you guys to try it out and try the scaffolding out. Because this scaffolding is a whole bunch of scaffolding from a whole bunch of areas. So it might be completely different later on, but as of right now, it's pretty good. It gives me good, runs well with Claude. It's always very quick. So you can see me doing Claude things in the back. Yeah, it's just making the databases a little bit better. But yeah, so that's where we stand right now. That's the iteration that we stand at. It says z.ai, but that's just because there's z.ai in the background with GLM running sometimes. This is actually called THESEUS, like the ship's THESEUS, because it comes around so many changes. What's the original? You know, who knows? It's like 20 different things. You should see there's like 20 different dashboards here. In the next couple of days, I'll start showing off the dashboards that it created. They're pretty cool, and they all track different things. Yeah. So if you have any ideas what to do, or add things in, or what I could do with this whole system in general, leave me a comment. Let me know. And yeah, talk to you guys later. Have a good one. See ya.